Theory of everything. In the world of physics, we've uncovered powerful laws, precise equations that can describe how planets move, how atoms behave, and even how the universe might have begun. But each of these laws operates within its own domain. One governs gravity, another explains quantum particles, and the two don't line up. This is where the idea of the theory of everything comes in. A single unifying framework, one ultimate equation that could bring all of nature under one roof. Every force, every particle, every interaction, from the bending of space-time to the construction of matter, explained by a single principle. But there's a major challenge. Despite decades of rigorous searching, we haven't found this equation. Einstein's general relativity gives us an extraordinary description of gravity. Quantum mechanics, meanwhile, unlocks the bizarre behavior of subatomic particles. But when we try to combine these two in extreme conditions, like the center of a black hole or the very first moment of the universe, the math completely breaks down. Ambitious theories like string theory, loop quantum gravity, and grand unification models aim to bridge the gap, yet none have been experimentally confirmed. So the question lingers: does the universe operate under one elegant rule we've yet to uncover? Or is it intrinsically fragmented? The theory of everything isn't just about merging equations. It's about unveiling whether all of reality dances to one hidden rhythm, or whether the final missing piece simply doesn't exist. Universe is missing antimatter. By the laws of known physics, the universe we live in shouldn't exist the way it does, not with its stars, galaxies, or even us. Right after the Big Bang, matter and antimatter should have been produced in equal quantities, and whenever these opposites meet, they annihilate each other in a burst of energy, a basic principle in particle physics. If matter and antimatter were perfectly balanced, they should have wiped each other out completely, leaving behind only radiation. But somehow that didn't happen. For reasons we still can't fully explain, there was just a minuscule excess of matter, roughly one particle more for every billion matter-antimatter pairs. And that tiny surplus, that's what formed everything, the galaxies, the planets, the atoms that make up our bodies. This strange imbalance is at the heart of a mystery called the Baryon asymmetry problem. Some experimental results have shown that matter and antimatter don't always behave symmetrically, an effect known as CP violation. However, the degree of asymmetry observed so far is far too small to account for the massive dominance of matter in the cosmos. Some theories suggest unknown processes occurred during the early universe. Others hint at hidden particles or interactions we haven't yet discovered. There's even the wild possibility of a mirror antimatter universe existing separately from ours, forever unreachable. For now, though, we're left with a profound riddle. The universe is here, but based on everything we know, it shouldn't be. The missing antimatter isn't just a gap in our equations. It's a quiet, persistent reminder that the foundation of existence rests on something we still don't understand. Fractal universe hypothesis. The universe is enormous, so vast it's beyond comprehension, stretching across billions of light years. But what if the universe isn't just vast? What if it's infinitely structured? What if it follows patterns that repeat themselves endlessly, no matter how deep you zoom in or how far you zoom out? That's the premise behind the fractal universe hypothesis. Fractals are repeating patterns that look similar across scales. Think of a tree. Large branches split into smaller ones, which split again, and each level resembles the whole. You find fractals everywhere in nature, in clouds, coastlines, mountains. In mathematics, they represent perfect self-similarity. The fractal universe idea takes this to a cosmic level, suggesting that everything from subatomic particles to clusters of galaxies might follow the same repeating geometry. At first glance, it seems almost too abstract to be taken seriously. How could the entire universe, with all its complexity, obey a pattern so simple? Yet some physicists point to the actual distribution of galaxies, which isn't uniform. Instead, galaxies tend to form in massive webs and clusters separated by enormous voids, patterns that bear a striking resemblance to fractals. If the fractal model holds true, it would mean the universe has no final scale, no top or bottom, just endless complexity layered upon complexity. Looking deeper into space could be just like looking deeper into the same pattern, looping forever. Could this be the true structure of reality? If so, we might be staring at a universe built on an infinite blueprint, a design we've only begun to glimpse. The fractal universe remains an unproven hypothesis, but it opens a breathtaking door to how we might understand the cosmos. Emergence of consciousness and physics. What if the thing that makes you you, your thoughts, your emotions, your awareness, could all be explained through the laws of physics? As wild as it sounds, some scientists believe that consciousness might not be a mystical force, but rather something that naturally arises from the deep structure of reality. The idea is simple, but profound. Complex systems like the brain can generate conscious experience by linking together simpler physical processes. In this view, consciousness isn't some magical spark. It's an emergent property of neurons firing and interacting in immensely intricate ways. But here's where things get mysterious. Even after decades of research, we still don't fully understand how physical brain activity produces subjective experience. Why does a collection of cells thinking and transmitting electrical signals result in the feeling of being alive? Enter quantum mechanics, the science of the very small, where reality starts acting in bizarre and unpredictable ways. Some researchers believe that quantum effects might be the missing piece. Theories suggest that tiny structures within brain cells called microtubules may host quantum states, giving rise to conscious thought in ways we can't yet grasp. This line of thought doesn't just bridge neuroscience and physics, it forces us to confront a deeper possibility, that consciousness might be woven into the fabric of the universe itself. Could awareness be more than just a physical byproduct? Might it be a fundamental component of reality, just like space, time, or energy? The truth remains elusive, but as we explore the boundary between physics and the mind, the emergence of consciousness might reveal not just how we experience the world, but why we experience it at all. Cosmic inflation instability. At the dawn of the universe, something extraordinary occurred. In a split second, the cosmos underwent an unimaginably rapid expansion, an event known as cosmic inflation. It wasn't just fast, it was faster than light, stretching space itself at a speed that reshaped everything to come. This inflationary burst laid the groundwork for the uniform universe we see today. Galaxies, stars, and cosmic structure all stem from that first expansion. But beneath this elegant theory lies an unsettling possibility. Could the very process that birthed the universe also carry within it the seeds of instability? According to some cosmologists, cosmic inflation might not be entirely stable. Under certain conditions, it could trigger another burst of inflation, creating what are known as pocket universes. These new universes would form independently, each with its own unique laws of physics. If true, our universe might be just one bubble in an infinite cosmic foam, where universes constantly bud off like droplets. This multiverse idea is speculative, but it raises haunting questions. What if this instability hasn't stopped? Could our universe ever experience a sudden change, another inflation event? What would happen to space, time, and everything in it? While such scenarios are theoretical, they force us to look at the universe not as a static backdrop, but as something dynamic and possibly fragile. The concept of cosmic inflation instability isn't just about origins, it's about whether the universe is as solid and unchanging as it appears, or whether we exist in a fleeting moment of calm, surrounded by deeper, unpredictable forces still at play. The arrow of time paradox. We live our lives moving from past to present and onward to the future, always feeling as though time flows in a single, unstoppable direction. But what if that flow isn't as absolute as it seems? What if time, as we understand it, is far more flexible than our everyday experience suggests? This is the heart of the arrow of time paradox, one of the most puzzling mysteries in modern physics. The paradox arises from the observation that time seems to move only one way. We remember yesterday, not tomorrow. We watch ice melt, but never unmelt, or a shattered glass never leap back into one piece. These irreversible processes give time its apparent direction. But here's where it gets strange. The fundamental laws of physics, the rules that govern motion, gravity, and even quantum particles, don't actually care which way time flows. They are symmetric, meaning they work the same whether time runs forward or backward. So why does time appear to march forward so relentlessly? The answer, as scientists believe, lies in the concept of entropy, a measure of disorder. As time passes, systems naturally evolve from order to disorder. A tidy room becomes messy, and hot coffee cools down. This rise in entropy gives time its one-way flow, a built-in direction that aligns with our everyday experiences. But while entropy explains the arrow, it doesn't explain why time is connected to entropy in the first place. This paradox has become a focal point for researchers exploring the foundations of reality. Could time be an illusion? Is there a deeper principle yet to be discovered that truly governs its direction? The arrow of time paradox challenges not only our scientific theories, but our very perception of how existence unfolds. Vacuum decay. Imagine living in a universe that seems calm and predictable, until in a blink everything changes. Not due to a cosmic explosion or a black hole, but because of a sudden collapse in the very fabric of space itself. This chilling idea is known as vacuum decay, a theoretical scenario that sounds like science fiction, yet is grounded in real quantum physics. In quantum field theory, what we call empty space isn't truly empty. It's filled with fields and energy fluctuations. Our universe may currently exist in what physicists call a false vacuum, a stable enough state, but not the absolute lowest energy configuration possible. Think of a ball resting in a shallow valley. It seems stable, but it could roll into a deeper valley nearby. If such a transition occurred on a cosmic scale, the results would be catastrophic. If our universe were to decay into a true vacuum state, it would trigger a bubble of new physics expanding at the speed of light, rewriting the laws of nature as it passed through. Inside that bubble, atoms might not form, light might behave differently, and matter as we know it could cease to exist. Worse still, this could happen without any warning and without any way to detect it until it's already too late. While current models suggest that vacuum decay is incredibly unlikely in our lifetime, or even in the lifetime of the universe, it remains a sobering concept. It reminds us that what feels like cosmic stability may be more fragile than we imagine. The potential for vacuum decay invites deeper questions about the long-term fate of our universe and the stability of everything we hold as constant. Phantom energy. Across the endless expanse of space, something unseen is accelerating the universe's expansion. This mysterious force is not just speeding things up, it may be pushing them to a terrifying extreme. Scientists call it phantom energy, and it might be the force that eventually rips the universe apart. For years, researchers have known that the universe is expanding. But what shocked everyone was discovering that the expansion isn't slowing down, it's actually speeding up. The driver of this acceleration is dark energy, which makes up about 70% of the universe. Phantom energy is a hypothetical, more extreme version of this force, one that grows stronger over time and could eventually dominate all cosmic interactions. If phantom energy exists, it could lead to a future scenario called the Big Rip. In this apocalyptic event, galaxies would drift so far apart that gravity could no longer hold them together. Stars would be torn from galaxies, planets would rip from their orbits, and even atoms themselves might eventually be pulled apart. The very fabric of space-time could unravel. The physics behind phantom energy is still uncertain. It may relate to the cosmological constant, a concept Einstein introduced in general relativity. Or it could point to something even more exotic that lies beyond our current theories. As scientists work to measure the rate of cosmic acceleration more precisely, they hope to determine whether phantom energy is real or just a mathematical anomaly. But if it's real, it may redefine everything we know about the future of the universe and its ultimate fate. Great Attractor Mystery. Deep in space, a mysterious force is dragging our entire galaxy and countless others toward a point we cannot fully see or understand. Known as the Great Attractor, this gravitational anomaly has puzzled scientists since its discovery, raising profound questions about hidden structures in the universe. The Great Attractor lies within the Laniakea supercluster, a vast region of space that includes the Milky Way. Despite our efforts, we can't directly observe this region, as it's hidden behind the zone of avoidance, a part of the sky obscured by the dense dust and stars of our own galaxy, yet its influence is undeniable. Galaxies, including our own, are speeding toward it at over 2 million kilometers per hour. What could possibly cause such a massive gravitational pull? Some researchers suggest it could be a titanic cluster of galaxies or a vast supermassive black hole. Others propose it might be a completely unknown structure or phenomenon, hinting at deeper cosmic truths we haven't yet uncovered. The true nature of the Great Attractor remains a mystery. We know it exists by its effects, but not by direct observation. Its powerful influence challenges our understanding of the large-scale structure of the universe and forces us to consider that there may be far more hiding in the dark corners of the cosmos than we currently comprehend. Dark flow. In the farthest reaches of the observable universe, something strange is happening. Galaxies aren't just drifting apart with the expansion of the universe, they're flowing in a mysterious, uniform direction. This unexplained movement is called dark flow, and it's one of the most unsettling anomalies in cosmology. First detected in 2008, dark flow describes a large-scale motion of galaxy clusters heading toward a region of space that lies far beyond what we can observe. This motion isn't caused by known gravitational forces from nearby galaxies or clusters. Instead, it's as if something outside the visible universe is pulling them, an unseen structure or force lurking in the cosmic darkness. The implications are profound. If dark flow is real, and not just a statistical error, it could indicate the presence of a massive cosmic structure beyond our horizon. Something we can't see or detect, yet powerful enough to influence the motion of entire galaxy clusters across billions of light years. Some scientists have even suggested that dark flow might hint at a multiverse, a collection of universes, each with its own laws of physics, with ours being just one among them. Others propose unknown forms of matter, or ancient cosmic remnants left over from before the Big Bang. While the evidence for dark flow is still debated, its possible existence pushes the boundaries of what we know and what we can imagine. It suggests that the universe might be part of a far larger, more mysterious reality than we ever thought possible. Supervoid in Eridanus. When astronomers pointed their telescopes at a region in the constellation Eridanus, they expected to see galaxies and stars. Instead, they found a vast emptiness, an enormous region nearly 1.8 billion light-years across, with almost no galaxies at all. This is the Eridanus supervoid. At first glance, it's just a cosmic desert. But then scientists noticed something even stranger. This void was affecting the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The area around the supervoid was colder than expected. Why? Some believe massive gravitational structures on the edges of the void are stretching space, draining energy from photons traveling through. Others wonder if it's evidence of something deeper, like a flaw in our understanding of dark energy, or even a cosmic scar from a universe beyond our own. The Eridanus supervoid isn't just a blank spot. It's a clue, a cold, quiet whisper in the dark, pointing to secrets the universe hasn't yet revealed. Bubble universe collision evidence. What if our universe isn't the only one? What if it's just one bubble in a vast cosmic foam, each bubble a universe with its own rules? That's the idea behind eternal inflation, and it leads to one wild possibility. Our universe may have collided with another. In 2007, researchers studying the cosmic microwave background noticed strange patterns, hot and cold spots that didn't fit with standard models. One explanation? A bubble universe bumped into ours, leaving a scar in space-time. These collisions, if real, would prove that the multiverse isn't just theory, it's reality. Each bubble could hold a different kind of physics, maybe even different kinds of life. While the evidence remains debated, the idea itself is revolutionary. It suggests we're not just a lone universe drifting in the void, but one of many, each with the power to change the others. The cold spot in the cosmic microwave background. When scientists first mapped the cosmic microwave background, CMB, they expected to find a nearly uniform glow. But one region stood out, a large area significantly colder than the rest. This became known as the cold spot, and it's one of the strangest features in cosmology. At first it seemed like a statistical fluke, but the size and temperature drop were too extreme. Some linked it to the Eridanus supervoid. Maybe the light passing through this emptiness lost energy. Others offered a more radical idea. Maybe the cold spot is the scar from a collision with another universe. Despite decades of study, the origin of the cold spot remains unclear. Is it just a rare blip in the early universe? Or is it a doorway to something deeper? A clue that we're not alone in the cosmic sea. The axis of evil. In 2005, scientists found a disturbing pattern in the cosmic microwave background. Temperature fluctuations, which should be randomly distributed, were strangely aligned along a single axis. This bizarre structure was nicknamed the axis of evil. Why is it so strange? Because it contradicts the assumption that the universe is the same in all directions. The Big Bang should have created a nearly uniform universe, but this alignment suggests something is off. Some suspect it's a data error. Others think it could be a sign of cosmic anisotropy. That space itself might have a preferred direction. And the most speculative theories? That it could point to another universe influencing ours. Whatever the cause, the axis of evil continues to haunt cosmology. It may be a fluke, or a sign that the universe isn't as random or as isolated as we once believed. White holes. We know about black holes, cosmic monsters that pull in everything, even light. But what about their opposites? Theoretical objects that expel matter and energy. These are called white holes, and they might be one of the most exotic phenomena in physics. White holes emerge naturally from the math of general relativity. Essentially, if you reverse time in a black hole's equations, you get a white hole. Instead of pulling in, they push out. But here's the mystery. While black holes have been observed, white holes have never been seen. Could they exist? Some theories suggest white holes might be linked to black holes, as if matter swallowed by one could reappear through the other, possibly even in another universe. Others tie them to wormholes or even time travel. White holes remain speculative, but their existence would reshape how we think about gravity, space, and the flow of time itself. They're a reminder that the universe might still hold surprises, hidden in equations we've only just begun to understand. Information paradox of black holes. Imagine tossing a book into a black hole. It disappears, swallowed by the darkness, gone forever. But here's the unsettling question that has puzzled scientists for decades. Where does the information in that book go? This conundrum is known as the information paradox, one of the most perplexing problems in modern physics. According to quantum mechanics, information about physical systems, like the arrangement of ink on the book's pages, can never truly be destroyed. Yet black holes seem to do exactly that. When matter falls in, it vanishes without a trace, as if its past form never existed. This poses a fundamental problem because it contradicts quantum theory's core principle of information conservation. On one side, we have the well-tested laws of quantum mechanics saying that information is preserved. On the other, general relativity tells us black holes erase that information. The paradox exposes a deep conflict between the two frameworks. Some theorists believe the information might be encoded on the event horizon's surface, an idea known as the holographic principle. Others suggest that as black holes slowly evaporate through Hawking radiation, they might leak the information back. Yet no one knows for sure. This unresolved mystery forces scientists to confront the very fabric of reality. Is information lost forever? Or is there a hidden law waiting to be discovered that connects the smallest particles to the largest structures in the cosmos? Black hole firewalls. We often picture black holes as cosmic traps, places where gravity becomes so intense that nothing, not even light, can escape. Crossing the event horizon is supposed to be quiet and uneventful, until the singularity crushes you. But what if instead that boundary hides something far more violent? What if there's a wall of deadly energy waiting, something known as a black hole firewall? This radical idea emerged to resolve a conflict between quantum mechanics and general relativity. Quantum theory insists that information cannot be destroyed. Yet if matter passes the event horizon and vanishes, that information seems lost forever. To preserve quantum laws, some physicists propose that the event horizon isn't smooth and passive, it's an inferno. A high-energy firewall could incinerate anything that crosses it, ensuring no information actually disappears. But this leads to a shocking contradiction. According to Einstein's theory, an astronaut falling into a black hole shouldn't notice anything unusual until reaching the singularity. The firewall theory challenges this, saying that person would instead be burned up instantly. If firewalls exist, they upend general relativity. If they don't, we're still stuck with the information paradox. The mystery of black hole firewalls remains unsolved, representing a critical test for any theory that tries to unite the physics of the very large with the quantum world. The answer could reveal not only the true nature of black holes, but the rules that govern the universe itself. Eternal inflation paradox. At the dawn of time, the universe exploded into existence through a burst of rapid expansion, what we call cosmic inflation. But what if that inflation didn't end? What if parts of the universe are still expanding at different rates, creating countless other universes in the process? This is the mind-bending concept behind the eternal inflation paradox. According to this theory, while our region of space stabilized into the universe we see today, other pockets of space kept inflating forever. Each of these inflating regions could give birth to separate bubble universes, possibly with their own unique physical laws. Our universe would then be just one of many in a vast, bubbling multiverse. But this raises deep and strange questions. If the process never ends, then the creation of new universes is happening all the time. How do we define now in such a system? How do we measure time in a cosmos where expansion never stops? It challenges our basic understanding of space, time, and observation. Furthermore, if each universe operates with its own rules, how can we ever hope to uncover any universal truths? The eternal inflation paradox suggests that reality may be infinitely bigger and stranger than we ever imagined. It's a riddle that forces us to reconsider not just where we are in the cosmos, but what the cosmos truly is. Universe as a neural network. What if the universe isn't just a vast expanse of stars, galaxies, and dark matter, but something far more intelligent? Some scientists and theorists have proposed a radical idea. The universe might function like a neural network, processing information in a way similar to the human brain. Neural networks are systems of interconnected nodes, like neurons, that work together to learn and adapt. This concept powers modern artificial intelligence. Now imagine that instead of silicon circuits, the universe itself is wired with galaxies and matter acting as nodes, exchanging information on a cosmic scale. It's not about the universe having a brain in a literal sense. Instead, it's the suggestion that information flows through the cosmos in complex, self-organizing patterns. The fundamental laws of physics, like gravity and quantum mechanics, could be the rules guiding this giant system's operation, just as synapses guide thoughts in a brain. Some even speculate that consciousness could emerge from such a universal network, or that what we think of as physical laws are the universe's own way of learning. While this idea remains speculative, it opens an intriguing window into how we interpret the cosmos. Could the universe be a vast intelligence, not just containing information but actively processing it? If so, we may be part of a system far more interconnected and possibly aware than we've ever imagined. The holographic universe hypothesis. What if everything you experience, sight, sound, touch, even time itself, isn't quite real, but a projection? This is the strange idea behind the holographic universe hypothesis. It proposes that the three-dimensional world we perceive is actually a 2D projection, like a hologram, encoded on a distant surface of space. While it may sound like science fiction, the theory has roots in real physics. It began with attempts to understand black holes, where scientists realized that all the information about what falls into a black hole might be stored on its surface rather than inside it. Extending this concept, physicists like Juan Maldacena proposed that the entire universe could work this way. Our reality, everything from galaxies to particles, could be a 3D projection of information stored on a two-dimensional cosmic boundary we can't see. If true, this would fundamentally reshape how we think about space and time. The objects and environments we interact with would be real to us, but might originate from a more basic informational layer. The mystery isn't just in the concept itself, but in how this could be tested and what it says about our place in the cosmos. Are we physical beings in a real space, or are we part of a grand illusion, an incredibly detailed projection on the edge of existence? The holographic universe hypothesis challenges us to question the nature of reality itself. Pair-instability Supernova. In the depths of space, stars live out their lives and end in explosive deaths, but some stars go out in a far more dramatic and mysterious way, through what's known as a pair-instability supernova. This rare phenomenon occurs in extremely massive stars, far larger than our Sun. As these giants burn through their fuel, their cores reach such high temperatures that they start producing pairs of particles, electrons and their antimatter counterparts, positrons. These pairs absorb energy, causing a sudden drop in pressure. Without that pressure, the star can't support its own weight. What follows is a massive explosion that completely tears the star apart. Unlike regular supernovae, which often leave behind a neutron star or black hole, a pair-instability supernova leaves nothing. The star is entirely obliterated. All that remains is an enormous burst of light and energy. These events are incredibly rare and difficult to detect, but they play a crucial role in the cosmos. They scatter heavy elements like gold and platinum across space, the same elements that eventually become part of planets and life. The mystery of the pair-instability supernova lies not just in its violent power, but in its rarity and importance to cosmic evolution. It reminds us that some of the most powerful forces in the universe also help create the building blocks of life. Boundary conditions of the universe. The universe is vast and expanding, but one question continues to haunt physicists. What lies at its edge? Or does it even have one? This question leads us to the mystery of the boundary conditions of the universe. When we say the universe is expanding, it's natural to wonder, what is it expanding into? Is there an edge, a boundary, where everything just ends? Or is the universe infinite, stretching on forever with no end in sight? One popular idea in physics suggests that the universe may have no boundaries at all. Instead, space might be curved in such a way that it loops back on itself, like the surface of a sphere. In such a model, if you traveled far enough in one direction, you'd eventually return to your starting point. But this still leaves many questions unanswered. If space has no edge, what exactly defines its shape? And what were the initial conditions at the moment of the Big Bang, the event that started it all? Things get even more complex when you consider theories about the multiverse. If our universe is just one of many, do other universes have different boundaries, or none at all? Could our universe be a bubble floating in a much larger structure? The search to understand the boundary conditions of the universe is a journey into the unknown, challenging everything we think we know about space, time, and reality itself. Exotic vacuum objects. Far beyond our solar system, deep in the vacuum of space, there may be strange and unpredictable entities known as exotic vacuum objects. These theoretical objects don't behave like anything we've ever seen. In fact, they may not follow the known rules of physics at all. What we once thought of as empty space, the vacuum, is now believed to be filled with energy fluctuations. These fluctuations might create bizarre new states of matter under extreme conditions. Some theories suggest that the vacuum of space could undergo a phase transition, much like water freezing into ice, giving birth to exotic vacuum objects. These could be dense, unstable, and potentially dangerous. They might grow, shift, or collapse, reshaping space itself as they move. Some versions of the theory imagine these objects as bubbles of strange matter that could consume or convert ordinary matter, much like a runaway chain reaction. What makes this concept even more disturbing is that we don't know whether these exotic vacuum objects already exist somewhere in the universe, or whether they might appear one day. If they do, they could challenge everything we know about space, energy, and even the laws of physics. Are these objects lurking in the corners of the cosmos, waiting to emerge? We don't know, but the mystery pushes scientists to look deeper into the strange and powerful forces hidden in the vacuum of space. Tachyonic fields. In the world of physics, nothing is supposed to travel faster than light, but what if that rule could be broken? This is where the concept of tachyons and tachyonic fields comes into play. Tachyons are hypothetical particles that might move faster than the speed of light. something that seems impossible under Einstein's theory of relativity. These strange particles would have what's called imaginary mass, meaning they don't behave like any known matter. If tachyons exist, they could form what's known as a tachyonic field, a field of energy spread throughout the universe based on particles moving faster than light. This idea has fascinated physicists, especially when trying to explain the rapid expansion of the universe after the Big Bang. Some theories suggest tachyonic fields could have triggered this explosive inflation, but it doesn't stop there. If tachyons really can move faster than light, could they also move backward in time? Could they allow for time travel or open the door to other dimensions? No one has observed a tachyon yet, and the concept remains highly theoretical. But the mystery of tachyonic fields challenges our understanding of speed, time, and the very nature of the universe, inviting us to question what's truly possible. Superluminal galactic jets. In the hearts of distant galaxies, powerful jets of energy shoot through space, and some appear to move faster than light. These are called superluminal galactic jets, and they're among the most mysterious and spectacular phenomena in the cosmos. These jets are made of plasma and are launched from the centers of galaxies, often near supermassive black holes. They can extend across millions of light years and travel at incredible speeds. Now here's the strange part. Some of these jets appear to be moving faster than light, but according to the laws of physics, nothing can exceed light speed. So what's going on? The answer lies in a visual trick caused by relativity. When a jet is moving close to the speed of light and is angled toward us, it can create an illusion that it's going faster than it really is, a phenomenon known as apparent superluminal motion. Even though the jets aren't truly breaking the speed of light, the effect is still shocking and puzzling. Why are these jets so powerful? How do black holes generate such extreme energy? These questions remain at the frontier of astrophysics. The mystery of superluminal galactic jets isn't just about speed. It's about the extreme environments near black holes and how they might reveal new truths about the nature of matter, energy, and space itself. Quasi-stellar objects, quasars' alignment. In the vast darkness of the cosmos, there exist dazzling beacons so luminous and distant that they seem almost unreal. Quasi-stellar objects, better known as quasars. Discovered in the 1960s, quasars are among the brightest and most energetic objects in the universe. They reside at the centers of distant galaxies and are powered by supermassive black holes actively consuming surrounding gas and dust. This intense feeding process generates radiation so powerful that a single quasar can outshine its entire host galaxy. But beyond their brilliance lies an even greater mystery: their unexpected alignment. Astronomers have observed that many quasars seem to be aligned along specific cosmic axes, pointing in similar directions across immense distances. This peculiar orientation defies the expected randomness of galactic distribution. Scientists are puzzled by this phenomenon and have proposed various theories. One idea is that these alignments may be the result of gravitational interactions with large-scale cosmic structures like galaxy clusters or dark matter filaments. Such interactions could be influencing the spin axes of black holes, creating these unusual patterns. However, what's particularly perplexing is that these alignments stretch over scales much larger than any single galaxy. This raises the possibility of an unknown force or fundamental principle shaping the universe in ways we don't yet understand. Could there be a hidden cosmic structure or law guiding the formation and direction of quasars across the cosmos? The mystery of quasar alignment challenges our current models and suggests that the universe may be far more interconnected and structured than previously imagined. The search for answers continues, pushing the boundaries of both astronomy and physics. Pioneer Anomaly. In the early days of space exploration, NASA launched the Pioneer 10 spacecraft in 1972, marking humanity's first journey beyond the outer planets. Its mission was to explore Jupiter and then drift silently into interstellar space. However, as Pioneer 10 traveled further from the Sun, scientists noticed something unexpected. The spacecraft was drifting slightly off its predicted path, slowing down in a way that couldn't be fully explained. This curious behavior came to be known as the Pioneer Anomaly, Initially, scientists thought the anomaly might be caused by malfunctioning thrusters or calculation errors, but after eliminating these possibilities through meticulous analysis, it became evident that the effect was real and unexplained. Pioneer 11, a twin spacecraft, launched later, exhibited similar behavior, confirming that the anomaly wasn't a one-time glitch. Some researchers proposed that heat radiating unevenly from the spacecraft might be causing a tiny push in the opposite direction, offering a partial explanation. Still, the anomaly raised more profound questions. Could there be an unknown force acting on spacecraft in deep space? Might the anomaly point to a flaw in our understanding of gravity, or even hint at a new physical principle? Some speculative theories suggest it could relate to dark matter or dark energy, mysterious components that make up the vast majority of the universe. While the anomaly is subtle, its implications are enormous. It reminds us that even small deviations can lead to major insights, and that our grasp of the universe's laws is far from complete. Flyby Anomaly. Gravity assists, slingshot maneuvers using a planet's gravity, are a cornerstone of spaceflight, allowing spacecraft to gain speed without expending fuel. But in several missions, spacecraft performing flybys around Earth and other planets have behaved unexpectedly, experiencing unexplained changes in speed. This oddity, known as the Flyby Anomaly, has left scientists scratching their heads for decades. The anomaly was first noticed in the 1990s, when spacecraft such as NASA's Galileo and ESA's Ulysses gained or lost a tiny amount of velocity during Earth flybys, more than calculations had predicted. At first, these discrepancies were thought to be the result of instrumentation errors or minor data misinterpretations. But when later missions like Rosetta and Cassini experienced similar anomalies, it became clear this wasn't an isolated incident. Numerous explanations have been proposed, from thermal emissions to gravitational modeling errors, but none have fully resolved the puzzle. Some theorists even suggest that unknown physical forces or undiscovered properties of space-time might be responsible. Could the anomaly indicate a deeper problem in our understanding of orbital mechanics or relativity, or is it a subtle but important clue hinting at new physics? Although the Flyby Anomaly affects spacecraft by only a tiny margin, its persistence across multiple missions suggests that we might be missing something fundamental. It's a quiet but powerful reminder that the cosmos still holds secrets that even our best instruments and models have yet to uncover. Oumuamua's non-gravitational acceleration. In October 2017, astronomers detected something unprecedented, an object named Oumuamua, hurtling through our solar system at incredible speed. Unlike any asteroid or comet observed before, Oumuamua's origin and behavior sparked intense debate and fascination. What truly baffled scientists, however, was its unusual acceleration. As it passed the Sun, it sped up in a way that couldn't be explained by gravity alone. Typically, comets accelerate due to the release of gas and dust when heated by the Sun, creating a visible tail. But Oumuamua had no such tail, no sign of outgassing or material shedding that could account for its change in speed. It was as though an invisible hand was gently pushing it along, defying standard models of motion in space. Some researchers proposed that sunlight pressure might be responsible, perhaps acting on a very thin, flat surface, leading to the wild theory that Oumuamua could be an artificial object, like a discarded solar sail or probe from another civilization. While this idea remains speculative, it highlights just how little we know about the vast array of objects that might be drifting through interstellar space. Adding to the mystery was its elongated, cigar-like shape and rapid tumbling motion. It didn't resemble any known comet or asteroid, suggesting that it might be a fragment of something much larger or entirely foreign. Oumuamua's brief visit raised more questions than it answered and challenged our assumptions about celestial mechanics. As the first known interstellar object to enter our solar system, it has left a trail of curiosity in its wake, pointing to mysteries we've only just begun to unravel. Quantum biology phenomena. Quantum physics, with its strange rules and paradoxes, typically belongs to the world of subatomic particles, not to living systems. Yet, a growing body of research is revealing a stunning possibility. Quantum mechanics might be at work in the processes of life itself. This fascinating intersection, known as quantum biology, is reshaping how we understand both physics and biology. One of the most compelling examples is found in photosynthesis. Plants convert sunlight into chemical energy with nearly perfect efficiency, far better than any man-made solar cell. Scientists believe this may be due to quantum coherence, allowing energy to travel through the plant's molecular structures via multiple pathways simultaneously. Selecting the most efficient route in a process classical physics can't explain. Quantum effects may also help migratory birds navigate using Earth's magnetic field. It's proposed that certain proteins in their eyes, entangled at a quantum level, allow them to see magnetic fields and orient themselves during long-distance flights. If confirmed, this would mean birds are essentially using quantum entanglement, a concept so bizarre that Einstein once called it spooky action at a distance. Even human biology might not be exempt. Enzymes, olfaction, sense of smell, and even DNA mutations could involve quantum processes. Though still a developing field, quantum biology raises a profound question. Is life as we know it built upon the strange, probabilistic rules of the quantum realm? As scientists dive deeper, they may uncover not only new insights into life on Earth, but also entirely new ways of thinking about consciousness, evolution, and the very nature of existence itself. Quantum consciousness interaction. What if the very act of thinking, the awareness behind your thoughts, was somehow tied to the strange and unpredictable world of quantum mechanics? It's a mind-bending idea that's captured the curiosity of both scientists and philosophers. At first glance, the brain seems to operate through classical biology, neurons firing, chemicals transmitting signals. But some researchers propose that quantum processes may actually play a role in consciousness itself. In quantum mechanics, particles can exist in multiple states at once, or even influence each other across vast distances instantly. Could such bizarre behaviors be quietly shaping the way our minds work? This theory gained attention through the work of physicists like Roger Penrose and Stuart Hameroff, who proposed that quantum events could be taking place inside microtubules, tiny structural components within brain cells. According to their idea, these structures might support quantum effects that contribute to thought, memory, and even self-awareness. But how could this happen in the brain's warm, wet, noisy environment, conditions usually considered too chaotic for delicate quantum states to survive? That's what makes the idea so mysterious. If quantum states do exist within the brain, they might reveal something entirely new about how consciousness arises. Are we tapping into a deeper layer of physical reality when we think, dream, or perceive the world? Or are we merely seeing patterns where none exist? While the theory remains controversial, it pushes the boundaries of how we understand both the mind and the universe. If true, it might mean that the very essence of consciousness is far stranger and more fundamental than we ever imagined. Quantum retrocausality. In the classical view of time, the past causes the present and the present shapes the future, cause and effect in a straight line. But in quantum mechanics, time doesn't always behave so neatly. Enter quantum retrocausality, a deeply puzzling idea suggesting that future events might influence the past. This concept challenges the very structure of reality and flips our understanding of time on its head. One of the most famous experiments tied to this idea is the double-slit experiment, where particles act like waves or particles depending on how and whether they're observed. Some interpretations suggest that a decision made in the present, like choosing to observe the particle, can retroactively influence what the particle did in the past, as though the future reached back to affect history. It's as if time isn't a one-way street, but something much more complex and flexible. If retrocausality is real, then we might have to rewrite our most basic assumptions about time and causation. Could future choices really shape past events? Are we part of a universe where timelines loop and twist in unpredictable ways? Testing this idea is a monumental challenge, but it forces us to question the nature of time, choice, and observation. If the future and past are more connected than we believe, then the universe might be playing by rules far stranger than anything we've imagined. Quantum immortality. What if death isn't the end? What if in some form you always survive, just in another version of the universe? That's the eerie promise of quantum immortality, an idea born from the many worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event has multiple possible outcomes, reality splits. Every possibility becomes real in its own parallel universe. Now imagine you're in a life-threatening situation. According to quantum immortality, in one universe you might die, but in another, one where the fatal event doesn't happen, you survive. From your own point of view, you always find yourself in the branch where you live. Death then may only occur from an outside perspective, never from within your own consciousness. This theory challenges everything we think we know about life and death. If your awareness always continues, are you essentially jumping from one branch of the multiverse to another, endlessly surviving in some reality? Could death simply be a transition, a shift in perspective, rather than a true end? While this remains highly speculative, it raises profound questions about existence, consciousness, and what it truly means to be alive. Quantum suicide. Quantum suicide builds on the unsettling idea of quantum immortality, but in a darker, more extreme way. Imagine facing a test of survival, where each outcome is determined by a quantum event. According to the many worlds interpretation, every possible result creates a new universe. So in a setup where a quantum process determines whether a gun fires or not, one universe sees the subject die, but in another, the subject survives. From the subject's perspective, they always end up in the reality where they live. No matter how many times the experiment is repeated, their experience is always one of survival, even if every other version of themselves perishes. It's a chilling idea, that consciousness only follows the path of survival, rendering death unobservable to the self. Quantum suicide isn't just a wild thought experiment. It forces us to confront the nature of life, death, and consciousness. Could our awareness be inherently tied to the act of survival? And if so, what does that say about the nature of our choices, our fates, and the multiverse we might unknowingly inhabit? Though entirely theoretical, the concept leaves a haunting question. Is death real, or just a split we never experience? Quantum Zeno effect. Imagine a particle in a box, ready to change states, to decay, transform, or move, but every time you check on it, you stop it from doing anything. This strange behavior is the heart of the quantum Zeno effect, where observation doesn't just reveal reality, it freezes it. In quantum physics, systems evolve over time in probabilistic ways, but when you measure a system constantly, something odd happens. The evolution slows, and in the extreme, stops entirely. It's as if the particle, aware of being watched, refuses to act. Experiments with atoms and photons have confirmed this surreal behavior. The more you observe, the more you trap the particle in its current state, halting time in its microscopic world. What makes this even more mysterious is the implication for larger systems. Could continuous observation affect how events unfold on larger scales? Could reality itself be influenced or even shaped by the act of conscious observation? The quantum Zeno effect offers a tantalizing glimpse into how deeply entangled observation might be with the very flow of time and change, suggesting that the boundary between the observer and the observed might not be as solid as we think. Quantum spin liquids. In the realm of the ultra-small, where the rules of classical physics start to unravel, a peculiar and mind-bending state of matter exists, known as quantum spin liquids. Unlike ordinary solids or liquids where particles fall into ordered patterns, quantum spin liquids defy that expectation entirely. Here, even though the particles are locked into a solid structure, their quantum spins, a fundamental property like an internal compass, remain in a state of perpetual motion. These spins never settle or align, not even at absolute zero, the coldest temperature possible, where normally all motion should cease. First theorized in the 1970s, quantum spin liquids remained a purely theoretical curiosity until experimental evidence began surfacing in recent years, particularly in certain copper-based compounds. These materials exhibited behaviors that couldn't be explained by classical physics, hinting at this mysterious spin behavior. What makes them especially intriguing is their potential in future technology, from breakthroughs in quantum computing, where quantum bits or qubits could use these fluctuating states for more stable data storage, to new methods of manipulating magnetic fields, the possibilities are vast. However, because of their elusive nature and the complexity of detecting them, much remains unknown. Could quantum spin liquids unlock entirely new phases of matter? Or are they merely the beginning of an even stranger frontier in particle behavior? Emergence of time from quantum entanglement. Time at an ever-moving, seemingly constant flow governs every aspect of our lives. Yet, in the quantum world, time begins to lose its familiar meaning. Some physicists are now exploring the groundbreaking idea that time itself may not be fundamental, but something that emerges from the interactions of quantum particles. At the core of this concept is quantum entanglement, a phenomenon where particles become deeply linked. Their states so intertwined that a change to one affects the other instantly, regardless of distance. But what if these entangled interactions give rise to something as profound as time? In this view, time is not a pre-existing backdrop, but a byproduct of relationships between quantum particles. It's as if the act of being entangled creates a directional flow, the time we experience. That raises mind-bending questions. If time emerges from quantum interactions, could it mean there was once a state in the early universe where time simply didn't exist? Could the entire concept of past, present, and future be a kind of quantum illusion? Though still a developing theory, this idea challenges our deepest assumptions and may reshape how we understand the cosmos. If time is not a constant but a construct of quantum relationships, then the very fabric of reality might be more fluid and dynamic than we ever imagined. Negative mass effect. What if the universe held objects so strange they did the opposite of everything we expect? Picture an object that doesn't fall down when dropped. It rises. This bizarre concept lies at the heart of negative mass, a theoretical type of matter that breaks all conventional rules of physics. Under normal conditions, mass is always positive. It attracts other masses through gravity and resists motion according to Newton's laws. But negative mass flips this entirely on its head. If you push it, it doesn't move away. It accelerates toward you, like something out of a science fiction story. This reversal of motion challenges our fundamental understanding of force and momentum. Although no direct evidence of negative mass has been found, theoretical models suggest it could exist under exotic conditions. Some physicists speculate that dark energy, the unknown force accelerating the universe's expansion, might be linked to negative mass properties. If true, it could help explain one of the most confounding mysteries in cosmology. The real mystery lies in whether this strange form of matter could be real or just a curious result of mathematical equations. If negative mass exists, could it be harnessed? Could it power new types of propulsion systems or unlock entirely new fields of physics? For now, it remains one of the most mind-twisting and thought-provoking puzzles of modern science. Delayed choice quantum eraser. Imagine if your actions in the present could change the past. It sounds like a plot from a time travel movie, but in the quantum world, this is a real and experimentally observed phenomenon known as the delayed choice quantum eraser. It begins with the famous double-slit experiment, where particles like photons behave like waves or particles depending on whether they're observed. If you look to see which slit the photon went through, the interference pattern, a wave-like behavior, disappears, and the particle seems to choose a single path. Now the quantum eraser adds a twist. What if you decide whether to observe the path after the photon has already passed through the slits? Shockingly, your later decision seems to affect what the photon did earlier. This suggests that reality itself doesn't solidify until it's observed, even retroactively. The delayed choice quantum eraser creates a paradox. Can the future really influence the past? Does consciousness play a role in collapsing possibilities into reality? These results force us to reconsider our notions of time and causality. It challenges the idea that the past is fixed and unchangeable. In the quantum realm, it seems the universe is not just strange. It might be fundamentally non-linear, where reality itself depends on the choices we make, even after the fact. Non-locality without entanglement. Quantum physics has already shown us that particles can affect each other instantly across vast distances, a phenomenon known as entanglement. But what if such influence could occur even without entanglement? This is the mystery of non-locality without entanglement, a concept that pushes the boundaries of what we know about communication and connection in the universe. Traditionally, non-local behavior is tied to entangled particles. Measure one and the other instantaneously reflects the change, no matter how far apart they are. But some recent studies have hinted that particles can still show correlated behavior without being entangled at all. How is this possible? This unexplained connection suggests that there might be a hidden layer of physics, something deeper than entanglement, possibly involving unknown fields or unseen forces. If particles can affect one another without a shared history or entangled state, then space and time might be far more interconnected than we realize. The implications are staggering. Could the universe operate through a network of invisible relationships beyond what current physics can explain? Could there be a deeper form of quantum communication that bypasses even the limits of entanglement? This mystery urges scientists to search for new principles governing the quantum world, principles that could revolutionize how we understand space, time, and the interconnectedness of everything. Observer effect variations. What if simply watching something could change what it does? It may sound like science fiction, but in the strange, unpredictable realm of quantum mechanics, this is a well-documented phenomenon known as the observer effect. It suggests something truly mind-bending, that reality itself may be shaped or even altered by the act of observation. Take the classic double-slit experiment. When electrons or photons are fired through two slits without being observed, they behave like waves, creating interference patterns. But as soon as scientists observe which slit the particle travels through, the particle stops acting like a wave and instead behaves like a solid particle. The interference pattern vanishes. It's as if the particle decides how to behave based on whether it's being watched. But here's where it gets more mysterious. In certain variations of the experiment, observation seems to cause only minor or inconsistent changes, sometimes no change at all. Why does observation collapse the wave function in some cases and not in others? Could unknown factors be at play? Some physicists argue this could hint at a deep connection between consciousness and quantum systems, while others suggest it's a limitation in how we perform measurements. These variations challenge our understanding of reality. Could our minds, in some subtle way, be shaping the behavior of the universe? The observer effect and its inconsistencies remain one of the most perplexing quantum puzzles, one that might hint at an unseen link between the observer and the observed, a connection we are only beginning to comprehend. Quantum Cheshire Cat. Imagine looking at a cat, only to find its grin on one side of the room and its body on the other. It sounds like a scene from Alice in Wonderland, and that's exactly where this mind-twisting idea gets its name. Welcome to the world of the quantum Cheshire Cat, a phenomenon where a particle and its properties appear to separate, existing in different places at the same time. This bizarre effect emerged from an experiment where photons were passed through an interferometer, an instrument that splits particles into paths. Scientists discovered that while the photon itself seemed to take one path, its properties, such as polarization or spin, appeared to travel along another. Just like the Cheshire Cat's body and grin parting ways, a particle and its identity were found in different locations. This discovery breaks all our classical expectations. In everyday life, an object and its traits are inseparable. A spinning top has its spin, a cat has its tail. But in the quantum world, particles and their properties can become detached, behaving in ways that defy logical structure. What does this mean for our understanding of reality? Could it suggest that the fabric of the universe isn't made of indivisible things, but rather of traits and probabilities that shift and float independently? The quantum Cheshire Cat opens the door to radical ideas. Perhaps reality, as we know it, is far more fragmented and surreal than we ever imagined. Quantum foam. Beneath the seemingly smooth surface of space and time lies something completely chaotic. A turbulent, invisible storm of activity so small and so wild we can't see or touch it. This is quantum foam, an eerie concept that suggests that the very foundation of our universe is not solid or still, but wildly fluctuating. Quantum foam is believed to exist at the Planck scale, the smallest scale imaginable, far smaller than atoms or particles. At this level, space is anything but calm. Instead, it's a frothy sea of energy fluctuations where particles are constantly popping in and out of existence. Imagine the ocean's surface, but made up of pure quantum uncertainty, bubbling with temporary particles and micro-warpings of space-time. Though we can't directly observe quantum foam, its effects may be profound. Some theorists believe this strange foam could influence how gravity works, how black holes form, and even how the universe began. Could these microscopic jitters be the very threads from which the cosmos is woven? If space isn't smooth but foamy, what does that mean for everything built on top of it? Quantum foam suggests that reality is far less stable than it appears. It may be the missing link that connects quantum mechanics and general relativity, a key to unlocking the ultimate theory of everything. The measurement problem. Quantum mechanics is incredibly successful at predicting how particles behave. Yet, hidden at the core of this science is a riddle that refuses to be solved, the measurement problem. It's a mystery about how the blurry world of possibilities we call the quantum state suddenly becomes the concrete world we see. In the quantum realm, particles don't have definite positions or speeds. Instead, they exist in superpositions, a mix of all possible outcomes. An electron can be in multiple places at once until we measure it. Then suddenly it chooses a position. This transition, called the collapse of the wave function, is at the heart of the measurement problem. But why should the act of measuring cause such a dramatic shift? Does the particle somehow know it's being observed? Is it our consciousness collapsing the wave function? Or are we simply witnessing a deeper rule of the universe that we haven't yet uncovered? Different interpretations offer different answers. Some claim reality doesn't exist until it's observed. Others believe all outcomes happen in parallel universes. Either way, the measurement problem forces us to confront an unsettling idea. The universe might not be entirely objective. Our role as observers could be more important than we ever imagined. Scale relativity. What if the rules of physics themselves shift and bend, depending on how closely you zoom in or out? That's the provocative idea behind scale relativity, a theory that challenges our assumption that the laws of nature are the same at all scales. In our daily lives, physics seems simple. Gravity pulls us down, objects move predictably, and space appears smooth. But when we explore the microscopic world of quantum mechanics, those rules collapse. Particles behave erratically, time becomes fuzzy, and uncertainty rules. Scale relativity suggests that just as Einstein's relativity showed us that time and space are flexible on cosmic scales, something similar might be true at the smallest levels. Maybe reality isn't fixed, but changes with scale, like zooming into a fractal, where new patterns emerge with each level of magnification. This concept could be the missing piece in the puzzle of unifying general relativity with quantum physics, two theories that, so far, refuse to work together. Could scale relativity be the bridge that finally unites the universe's largest and smallest mysteries? The universe may not operate under a single rigid set of rules. Instead, it might be more like a dynamic system, evolving differently depending on the scale at which it's observed. The answers lie hidden in the layers of reality, layers we're only beginning to peel back. Virtual particles becoming real. In the quantum world, reality often defies common sense. One strange phenomenon is that of virtual particles, tiny, fleeting entities that pop in and out of existence in the blink of an eye. But here's the mystery. Could these virtual particles somehow become real? Virtual particles are not something we can observe directly. They exist briefly as part of quantum fields, borrowing energy from their surroundings and vanishing almost instantly. They're like quantum echoes, there for a moment, then gone. Normally, these particles are harmless, too short-lived to affect the world around them. But in certain conditions, they appear to have real effects. One such case is the Casimir effect, where two uncharged metal plates placed very close together experience a mysterious force pulling them inward, believed to be caused by virtual particles in the vacuum between them. It gets stranger. In high-energy physics experiments, it's been proposed that virtual particles can gain enough energy to stabilize and become real, permanent particles. This process could give rise to entirely new forms of matter. So if virtual particles can become real under the right conditions, what does that say about the boundary between existence and non-existence? Could the rules of reality be more fluid than we think? This mystery invites us to look deeper into the unseen layers of the universe and maybe into what it really means for something to exist at all. Bimetric gravity, the invisible force that binds the cosmos, has always puzzled scientists. Einstein's theory of general relativity describes how mass bends space-time, creating gravity. It works beautifully for stars, planets, and galaxies. But zoom into the quantum world and things stop adding up. Enter bimetric gravity, a mysterious idea that suggests there might not be just one space-time geometry, but two. According to this theory, the universe could be governed by two separate metrics or ways of measuring space and time. One metric explains the familiar large-scale gravity we see in the cosmos. The other might operate in the quantum realm, where particles behave in strange, unpredictable ways. This dual metric setup could be the missing piece that helps bridge the gap between general relativity and quantum mechanics, two powerful theories that don't currently agree. Bimetric gravity might even explain phenomena like dark matter or the odd behavior of black holes. Could these two interacting spacetimes be the hidden structure of the universe? If true, it would mean our current understanding of gravity is only part of a larger, more complex picture, one that connects the immense with the infinitesimal. Einstein-Cartan Theory. Einstein's general relativity revolutionized our understanding of gravity, but what if there's more to the story? The Einstein-Cartan Theory offers a bold twist. What if spin, a fundamental property of particles, also influences the shape of spacetime? In this theory, not only mass but spin, the intrinsic angular momentum of particles, can twist spacetime. This twist, called torsion, adds an extra layer to the fabric of the universe, potentially explaining mysteries that general relativity alone can't solve. For instance, in extreme environments like the core of a black hole or the early universe just after the Big Bang, the role of spin and torsion might be crucial. It could even help explain the nature of dark matter or hint at new dimensions we haven't discovered yet. While still a developing theory, Einstein-Cartan suggests a fascinating possibility: that the universe is shaped not just by the mass of things, but by their spin as well. If so, gravity might be far more complex and far more mysterious than we ever imagined. Double special relativity theory. Einstein's special relativity tells us that space and time are flexible, depending on how fast you're moving. But what if the universe has two fundamental speed limits, not just one? This is the idea behind double special relativity, DSR. It keeps the speed of light as a cosmic speed limit, but adds another limit related to the smallest scales of space and time, where quantum effects dominate. DSR suggests that space-time itself might behave differently at extremely high energies, like near black holes or during the Big Bang. At those scales, the usual rules of physics may no longer apply in the same way, and space and time might start to warp in unexpected directions. This theory could help us understand why quantum mechanics and general relativity clash. It offers a possible bridge between the two, hinting that there might be hidden layers of reality we haven't yet explored. Could this be the key to solving deep cosmic mysteries like dark energy or the nature of time itself? Double special relativity invites us to question whether the universe is far stranger and more flexible than we thought. Mass gap problem. In the vast world of particle physics, there's a haunting mystery known as the mass gap problem. Simply put, there's a strange missing region between the lightest and heavier particles, like a gap where something should be, but isn't. We have very light particles like photons. We also have heavier ones like protons. But in between, strangely, there don't seem to be any stable particles. Why? The Standard Model explains how particles and forces interact, and it works incredibly well. But the mass gap, this no man's land of missing particles, suggests we might be overlooking something fundamental. Some physicists think that unknown particles could exist in this gap, bound together by forces we don't yet understand. If they're real, these particles might help explain dark matter or other unexplained cosmic phenomena. Solving the mass gap problem isn't just about finding a few missing particles. It could change everything we know about the forces that govern reality. This unanswered question sits at the core of modern physics, daring us to dig deeper into the hidden structure of the universe. Higgs boson metastability. In 2012, scientists made a major breakthrough at CERN with the discovery of the Higgs boson, the particle responsible for giving mass to other particles. It was a huge leap in understanding how the universe is structured, but hidden within that discovery is a strange possibility that the Higgs boson might not be fully stable. This idea, called metastability, suggests the Higgs field could someday shift into a different state, changing the universe entirely. Think of the Higgs field as a ball resting in a valley, stable and unmoving. But what if that valley isn't the deepest one? If the field ever rolled into a deeper valley, it could trigger a cosmic chain reaction that alters the very fabric of reality. The good news is this wouldn't happen anytime soon. Calculations show it would likely take billions of years, if it ever happens at all. Still, the idea is unsettling. Are we truly in a stable state, or could everything change one day? Even though current experiments suggest the Higgs boson is stable, there's a possibility it's just temporarily so. This mystery forces us to ask whether the universe is more fragile than we ever imagined. Axion dark matter experiment results. For decades, scientists have known that most of the mass in the universe isn't made of the kind of matter we can see. This invisible stuff, called dark matter, makes up around 85% of the universe's total mass. One of the most promising candidates for what dark matter could be is a theoretical particle called the axion. Axions are incredibly light and barely interact with anything, making them almost impossible to detect. But if they exist, they could help explain where all this missing mass comes from. Recently, researchers conducted a sensitive experiment looking for signs of axions, and something unusual happened. They found signals that didn't match any known sources. These results aren't solid proof yet, but they are exciting. They suggest we might be close to confirming that axions are real, and that they could be responsible for dark matter. The question now is whether these signals truly come from axions, or if there's another explanation we haven't found yet. Either way, this could be the first big step in solving one of the greatest mysteries in physics. Chameleon particles. Imagine a particle that can change how it behaves depending on its surroundings, just like a chameleon blending into its environment. This is the idea behind chameleon particles, a mysterious concept in modern physics. These particles are thought to be able to shift their properties based on the amount of matter or energy around them. They might be very noticeable in areas with high mass, like around planets or galaxies, but nearly invisible in empty space. That makes them hard to detect, which is one reason they've stayed a mystery. Chameleon particles were originally proposed to help explain dark energy, the strange force pushing the universe to expand faster and faster. If they exist, these particles could help answer why the expansion of the universe behaves differently in different regions. But despite efforts to find them, no one has yet detected chameleon particles directly. Still, the idea raises deep questions about what might be hiding in the empty spaces around us, forces and particles that are shaping our universe while remaining just out of sight. Gran Sasso faster than light neutrinos. In 2011, something happened that shook the world of physics. At the Gran Sasso laboratory in Italy, scientists working on the OPERA experiment thought they had observed neutrinos traveling faster than light. If true, this would break one of the most basic rules of Einstein's theory of relativity, that nothing can move faster than the speed of light. Neutrinos are tiny, barely detectable particles that usually pass through matter without interacting. In this experiment, a beam of neutrinos was sent from CERN to Gran Sasso, over 700 kilometers away. But when the data came in, it looked like the neutrinos had arrived slightly too early, as if they had broken the cosmic speed limit. The result caused a massive stir, but soon questions arose. Could the data be wrong? After careful checks, scientists found a problem in the timing equipment. A loose cable had caused the error. Once fixed, the neutrino's speed lined up with Einstein's theory after all. Even though it turned out to be a mistake, the event reminded scientists of how fragile our current understanding can be, and how easily it might be overturned by a surprising discovery. Neutrino flavor oscillation. Neutrinos are some of the most mysterious particles in the universe. They're extremely small, almost without mass, and they barely interact with anything. But there's something even stranger about them. They can change identities as they travel. This behavior is called neutrino flavor oscillation. There are three types, or flavors, of neutrinos: electron, muon, and tau. Scientists once thought that a neutrino, once created in one flavor, would always stay the same. But in the late 1990s, experiments showed that neutrinos could switch between flavors during their journey. This discovery was shocking because for such a change to happen, neutrinos must have mass, something that wasn't originally expected. Understanding how and why this transformation happens is still a mystery, but it has huge implications for our understanding of matter and the universe. Scientists continue to study neutrinos coming from the sun, nuclear reactors, and even distant supernovae. The more they learn, the more questions arise. What hidden forces allow these particles to switch identities? Could they help explain how matter came to dominate over antimatter in the early universe? The mystery is far from solved, but it might hold answers to some of the universe's biggest secrets. Lorentz Violation. Imagine a world where the speed of light isn't constant, and the rules of space and time behave differently than we thought. This is the mystery of Lorentz Violation. For over a century, Einstein's theory of special relativity has been one of the cornerstones of physics. It states that the speed of light is always the same, no matter your position or motion. This idea shapes everything from GPS to our understanding of space. But what if it's not entirely correct? Lorentz Violation suggests that under extreme conditions, the laws of physics might break down, and the speed of light could actually vary. Scientists first noticed small hints of this while studying high-energy particles. Some of these particles behaved in ways that didn't match relativity's predictions, as if the fabric of space-time was bending in subtle, unexpected ways. Researchers are now running experiments using cosmic rays and particles near light speed to find more evidence. If proven true, Lorentz Violation could help connect quantum mechanics with relativity, a long-standing goal in physics. It raises a deeper question: is our understanding of space-time incomplete? Could there be hidden layers of reality we've yet to uncover? Muon anomaly. In the world of particle physics, even small differences can lead to big questions. One such mystery is the muon anomaly, also known as the muon G2 experiment. Muons are particles similar to electrons, but heavier and unstable. In the 1960s, scientists noticed something odd. When muons moved through magnetic fields, they didn't spin quite the way expected. Years later, experiments like the one at Fermilab in Illinois studied this behavior more closely. They found that muons were behaving in a way that didn't fully match the predictions of the Standard Model, the theory that explains particle physics. This small difference suggests there might be a new unknown force or particle influencing the muons. It could even hint at connections to dark matter or hidden dimensions. While the results have excited the scientific community, more research is needed. Could this be the first sign of new physics, or just a strange fluke? The muon anomaly might be pointing us toward discoveries that could rewrite our understanding of the universe. Gravitational anomalies on Earth gravity is something we usually think of as constant, but in certain places on Earth, it behaves strangely. One of the most famous cases is the Hudson Bay anomaly in Canada. Here, gravity is noticeably weaker than expected. It's as if something is missing beneath the surface. At first, scientists thought it was due to low-density rock or simple geology, but further study revealed that it didn't add up. One theory is that ancient processes deep within the Earth left behind this strange gravitational signature. Another idea is that mantle movements might be causing it. But there's a more mysterious possibility: dark matter. Some researchers wonder if this elusive substance, which makes up most of the universe's mass, could be influencing Earth's gravity in subtle ways. This anomaly forces us to ask, are there hidden forces at work beneath our feet? The Hudson Bay anomaly remains an unsolved puzzle. Earth's hum. Have you ever heard a low, strange hum with no clear source? You're not alone. This is known as Earth's hum, a mysterious vibration felt and heard by people around the world. The hum is a low-frequency sound, around 10 Hz. Most people can't hear it directly, but some feel it or pick it up faintly. It's been recorded in cities, oceans, and even remote areas. Its cause remains unknown. Some scientists think it could be related to tectonic movements, small vibrations too weak to be called earthquakes. Others blame atmospheric or oceanic activity, where natural forces generate low sound waves. Interestingly, some suggest that human-made sources like machines or traffic could contribute. But the hum is often strongest in isolated areas, far from cities. Could the Earth itself be producing this sound, or is something else at play? The Earth's hum remains one of our planet's most puzzling phenomena. Ball lightning formation. Picture this. A thunderstorm rages, lightning strikes, and suddenly a glowing ball of light floats in the air. This bizarre phenomenon is called ball lightning, and it remains one of nature's strangest mysteries. Ball lightning has been reported for centuries. Unlike regular lightning, it can hover, move unpredictably, pass through walls, and disappear just as quickly. These glowing orbs can last several seconds and vary in size. No one knows exactly how they form. Some theories suggest they're made of plasma, electrically charged gas, but how this plasma stays stable is unclear. Others think magnetic fields or rare chemical reactions during storms might be involved. Scientists have tried to recreate ball lightning in laboratories, but none have succeeded so far. Could understanding this phenomenon help us learn more about energy, electricity, or even unknown forces in nature? Ball lightning remains a glowing mystery, one that challenges the limits of atmospheric science. Electromagnetic anomalies at Halen Valley. In a remote Norwegian valley known as Hessdalen, something extraordinary has been puzzling scientists and locals alike for decades. Strange glowing lights regularly appear in the night sky, floating, darting, and sometimes hovering in place. These luminous orbs, known as the Hessdalen lights, don't behave like any known aircraft or natural light phenomenon. Some lights remain stationary for minutes before vanishing, while others zigzag with incredible speed, almost suggesting some form of intelligent movement. Witnesses have described them as white, yellow, or even blue, sometimes appearing close to the ground and other times high above the valley. What makes the mystery deeper is its consistency. These lights have been observed regularly for over a century. Long before modern aircraft or drones, multiple scientific expeditions have attempted to document and study them. Some theories point to unusual electromagnetic activity possibly caused by local geology. Hessdalen sits atop metallic mineral deposits that might interact with the Earth's magnetic field. Other hypotheses include plasma formations from ionized gases, natural battery effects caused by underground elements, or rare atmospheric conditions. Still, none of these fully explain the frequency, motion, or intensity of the lights. More fringe theories even suggest unknown forms of energy or interdimensional activity, though these remain highly speculative. What's most fascinating is that these anomalies occur in one specific place, while similar regions show no such activity. Despite years of monitoring with radar, spectrometers, and cameras, the lights remain unexplained. As scientists continue to explore the mystery, Halen Valley stands as a reminder that Earth still holds secrets, forces in the natural world that may not yet fit into our scientific frameworks. Spontaneous human combustion. It's one of the most chilling and bizarre phenomena ever reported. Individuals found burned to ashes with little to no damage to their surroundings. This is the mystery of spontaneous human combustion, SHC, an event where a person appears to ignite and burn from within, without any clear external source of flame. Accounts of SHC span centuries, with victims often found in a sitting position, their torsos and limbs reduced to ash, while nearby furniture remains strangely untouched. The most confounding detail. In many cases, the fire seems highly localized, intense enough to incinerate a human body, which normally requires temperatures above 1,000 degrees, yet fails to spread. Some scientists have tried to offer rational explanations. The wick effect is one. If a person becomes unconscious near an ignition source like a cigarette, their clothing could act like a candle wick, drawing body fat as fuel. This could, in theory, produce a slow-burning fire that consumes the body without destroying the room. Another idea involves metabolic imbalances. Some researchers speculate that high concentrations of flammable substances in the body, like acetone from ketoacidosis, could make spontaneous ignition more likely. Yet these theories can't fully explain all cases, especially those with no clear ignition source. Skeptics argue that most SHC cases involve overlooked external flames, but that doesn't account for the consistency of the pattern across cultures and eras. Could there be unknown biochemical or quantum processes triggering a hidden ignition under rare conditions? As unsettling as the idea sounds, spontaneous human combustion remains an unsolved riddle, perhaps one that blends biology, chemistry, and physics in a way we still don't fully understand. Sun's corona temperature anomaly. The Sun is our nearest star, but even after centuries of study, it still holds secrets, perhaps none more puzzling than the corona temperature anomaly. The corona, the Sun's outermost layer, glows faintly during solar eclipses and extends millions of kilometers into space. But here's the strange part. It's hotter than the Sun's surface, much hotter. While the surface of the Sun, the photosphere, is about 5,500 degrees C, the corona reaches over 1,000,000 degrees Celsius. This flies in the face of basic thermodynamics. Normally, as you move away from a heat source, temperatures drop. So why does the temperature suddenly spike just beyond the surface? One possible explanation lies in the Sun's magnetic fields. These powerful dynamic fields might be transferring vast amounts of energy to the corona, possibly through a process known as magnetic reconnection, where twisted magnetic lines suddenly snap and release energy explosively. Another candidate is Alfvén waves, ripples in the Sun's plasma caused by magnetic disturbances. These waves could be carrying energy from the Sun's interior outward, then somehow dumping it into the corona. Yet despite this theory's elegance, the exact energy transfer mechanism remains unclear. The corona isn't just a curiosity. It plays a crucial role in producing solar wind, streams of charged particles that impact Earth's magnetic field and technology. Understanding why the corona is so hot could improve predictions of solar storms, which threaten satellites, power grids, and communication systems. For now, the mystery remains. The corona's extreme heat stands as one of the biggest open questions in astrophysics, proof that even our own Sun still has secrets we've yet to uncover. Titius-Bode Law Mystery. In the 1700s, a curious mathematical pattern emerged, a formula that appeared to predict the distances between planets in the solar system. This became known as the Titius-Bode Law, and for a time, it seemed almost magical. The rule is deceptively simple. Starting with Mercury, each planet's distance from the Sun can be approximated using a sequence involving doubling numbers. Astonishingly, it predicted the location of Uranus before it was discovered, and even pointed to a gap between Mars and Jupiter, where the asteroid belt was later found. For a while, it looked like the universe itself was organized by a hidden numerical rhythm. But then came Neptune and Pluto, which didn't fit the pattern. Suddenly, the law's predictability began to break down. So what is it? A cosmic coincidence, a numerical trick, or a window into a deeper, unseen structure in the formation of planetary systems? Some scientists think the Titius-Bode law reflects natural spacing due to gravitational interactions during the early solar system's formation. Planets may settle into stable orbits following a kind of mathematical resonance. But why those specific distances? And why does the law seem to work only for part of the solar system? Modern studies of exoplanet systems show some similar spacing patterns, but none match the neat regularity Titius and Bode described. Could this suggest a universal blueprint for planetary arrangement, or just the human mind searching for order in chaos? While dismissed by many astronomers today, the mystery lingers. The Titius-Bode law stands as a mathematical ghost, hinting that perhaps the architecture of our solar system is more than just random chance. Fermi Bubbles. In the heart of the Milky Way, far beyond what our eyes can see, something colossal and mysterious lurks, massive glowing structures stretching above and below the galactic plane. These are the Fermi Bubbles, a pair of gigantic energy-filled regions that have puzzled astronomers since their discovery in 2010. First detected by NASA's Fermi Gamma-ray Space Telescope, these enormous symmetrical bubbles extend roughly 25,000 light-years in both Directions: glowing brightly in gamma-ray light. Radiation so powerful it usually marks the presence of extreme cosmic events. But what caused them to form? That question has remained unanswered for over a decade. The sheer size and energy of the Fermi Bubbles suggest that something massive occurred in the center of our galaxy, something powerful enough to send waves of energy across tens of thousands of light-years. One theory points to our galaxy's central supermassive black hole. Scientists believe that as matter spirals into this black hole, it could occasionally erupt with powerful jets of energy, shooting out vast amounts of radiation and creating the twin bubbles we now see. But there's a catch. If these bubbles came from the black hole, why haven't we seen similar structures in other galaxies? And why don't we have direct evidence of such a dramatic event in the Milky Way's history? Another compelling possibility adds even more intrigue. Some researchers think the bubbles could be tied to dark matter, an invisible and poorly understood substance that makes up most of the universe's mass. If dark matter interacts in unusual or unknown ways, those reactions might explain the strange sustained gamma-ray glow. Could we be witnessing dark matter revealing itself not through what we can see, but through its powerful hidden effects? The mystery only deepens as more observations are made. These bubbles don't match any clear pattern, and their structure remains unusually clean and symmetrical for something so chaotic and ancient. Could this be evidence of a long-lost cosmic explosion? Or are we glimpsing an exotic process that lies beyond the boundaries of modern astrophysics? The Fermi bubbles aren't just a scientific puzzle. They're a haunting reminder of how much remains hidden in our galaxy. As telescopes grow stronger and data grows deeper, astronomers hope to uncover the origins of these mysterious giants. Until then, the Fermi bubbles float silently above and below the Milky Way, casting an eerie glow across space, quiet witnesses to an event or force we have yet to understand. Ghostly ring of dark matter. Amid the unfathomable expanse of the cosmos, scientists have stumbled upon a chilling mystery, one that defies conventional understanding and stretches the limits of astrophysical theories. It's called the ghostly ring of dark matter, and though it sounds like something from a science fiction novel, it's a real phenomenon grounded in cutting-edge physics. Dark matter, the elusive and invisible substance that makes up an estimated 85% of the universe's mass, doesn't emit light, energy, or radiation. We can't see it directly, but we know it's there because of its gravitational pull on visible matter. Now, astronomers have discovered something even more unnerving. A massive ring-shaped structure that appears to be composed entirely of dark matter, eerily circling around galaxies. Unlike anything we've encountered before, this ghostly ring exerts a gravitational influence that warps space around it. Yet it remains undetectable to traditional instruments. It's as if an invisible force is silently sculpting the universe, shaping galaxies in ways we don't fully comprehend. What makes this ring so strange is that it doesn't conform to the typical models of how galaxies form or behave. It doesn't match the shape, scale, or behavior of regular matter-based structures like galaxy clusters. Instead, it floats like a phantom halo, silent, vast, and inexplicable. Some researchers suggest that this ring may be the remnant of a massive collision between galaxies, where the dark matter retained a distinct ring shape while the visible matter was flung elsewhere. Others suspect it could be the sign of previously unknown dark matter interactions that don't fit within any established theory. Even more puzzling is the idea that this ghostly ring could date back to the early moments of the universe, making it a relic from a time when the cosmos was still taking shape. If that's true, studying it could reveal unprecedented insights into the birth and evolution of everything we know. But right now it raises more questions than answers. Is dark matter capable of forming its own complex structures? Could these rings exist elsewhere, hidden all across the universe? And are we only scratching the surface of something far deeper and stranger? The ghostly ring of dark matter continues to haunt scientific inquiry. It challenges what we think we know about gravity, structure, and the invisible scaffolding that holds the universe together. As researchers develop new techniques and technologies to probe the dark universe, the mystery of this ring lingers like a silent riddle, waiting to be solved, perhaps unlocking the secrets of the cosmos itself. Strange matter contagion hypothesis. सोचिए एक ऐसे मटेरियल के बारे में जो इतना अजनबी, इतना पावरफुल हो के अगर ये किसी भी नॉर्मल मैटर से टकराए तो उसे तुरंत अपनी तरह बदल दे। यही है स्ट्रेंज मैटर कंटेजन हाइपोथेसिस का डरावना तज्जिया। एक नजरिया जो सिर्फ साइंस फिक्शन का हिस्सा नहीं बल्कि रियल फिजिक्स के अंदर डिस्कस किया जा चुका है। स्ट्रेंज मैटर एक थियोरेटिकल सब्सटेंस है जो स्ट्रेंज क्वार्क्स पर मबनी होता है। ये क्वार्क्स आमतौर पर सिर्फ न्यूट्रॉन स्टार्स के अंदर या फिर हाई एनर्जी पार्टिकल कलिशंस के दौरान देखे गए हैं। अनलाइक ऑर्डिनरी मैटर जो प्रोटॉन्स, न्यूट्रॉन्स और इलेक्ट्रॉन्स से बना होता है, स्ट्रेंज मैटर को इतना स्टेबल और डेंस माना जाता है कि ये किसी भी चीज को छूने पर उसे अपनी तरह बना सकता है। यही है कंटेजन हाइपोथेसिस का सबसे खतरनाक पहलू। अगर ये मैटर किसी लैबोरेटरी एक्सपेरिमेंट या स्पेस कोलिजन के जरिए बांध जाए तो एक चेन रिएक्शन शुरू हो सकती है, एक ऐसी सिलसिलावार तब्दीली जिसमें हर मॉलिक्यूल, हर एटम स्ट्रेंज मैटर में बदलता चला जाए। इस थ्योरी के मुताबिक अगर ये रिएक्शन शुरू हो जाए तो वो रुकने का नाम नहीं लेगी। ये सिर्फ एक शहर या एक प्लैनेट को नहीं बल्कि पूरा यूनिवर्स को अपनी गिरफ्त में ले सकती है। सब कुछ, हम, ज़मीन, सितारे, सब एक बिल्कुल अजनबी सब्सटेंस में तब्दील हो जाएं। अब तक स्ट्रेंज मैटर का कोई ठोस सबूत नहीं मिला, लेकिन इस थ्योरी का वजूद ही इस बात का सबूत है कि यूनिवर्स में ऐसे अनजाने खतार मौजूद हैं जिनके हम अभी सिर्फ अंदाजा ही लगा सकते हैं। ये हाइपोथेसिस सिर्फ एक साइंटिफिक ख्याल नहीं है, ये एक रिमाइंडर है कि जितनी भी प्रोग्रेस हमने की है, अब भी कई मिस्ट्रीज ऐसे हैं जो हमारी समझ से बाहर हैं। स्ट्रेंज मैटर कंटेजन का खौफ सिर्फ थियोरेटिकल है, मगर इसका इम्पैक्ट इतना गहरा है कि ये हमें साइंस और एथिक्स दोनों में नए सवालत उठाने पर मजबूर करता है। वैक्यूम कैटास्ट्रोफी। तस्वीर कीजिए कि आप यूनिवर्स को एक खाली, पुरसुकून जगह समझ रहे हैं जहां कुछ भी नहीं है, सिर्फ खामोशी। लेकिन अगर वो खालीपन सिर्फ एक धोखा हो, अगर वो वैक्यूम जिसे हम खाली स्पेस कहते हैं असल में एक छुपी हुई एनर्जी से भरपूर हो जो किसी भी वक्त पूरे कायनात को तबाह कर सकती है, ये है वैक्यूम कैटास्ट्रोफी का राज। एक ऐसी साइंटिफिक गुत्थी जो क्वांटम फिजिक्स के दिल में छुपी है। क्वांटम मैकेनिक्स के मुताबिक वैक्यूम कभी भी वाकई खाली नहीं होती। उसमें क्वांटम फील्ड्स हमेशा फ्लक्चुएट करते हैं, पार्टिकल्स आते हैं और चले जाते हैं। ये छोटी फ्लक्चुएशंस वैक्यूम एनर्जी कहलाती हैं। मगर जब साइंटिस्ट्स ने यह एनर्जी कैलकुलेट करनी चाहिए, उनको जो रिजल्ट मिला वो ट्रिलियंस ऑफ टाइम्स ज्यादा था उस एनर्जी से जो हम रियल यूनिवर्स में महसूस करते हैं। ये इतना बड़ा फर्क है कि इसे वैक्यूम कैटास्ट्रोफी कहा गया है। सबसे बड़ी परेशानी ये है कि अगर थियोरेटिकल वैल्यू सही होती तो यूनिवर्स कब का कोलैप्स कर चुका होता। फिर यह कैसे मुमकिन है कि हम अब भी यहां हैं? कुछ फिजिसिस्ट्स कहते हैं कि हो सकता है वैक्यूम एक मेटास्टेबल स्टेट में हो, जैसे एक बॉल जो पहाड़ी के किनारे पर हो और कभी भी नीचे गिर सकती हो। अगर यह गिर गई तो एक नई एनर्जी स्टेट में ट्रांजिशन होगा जो स्पेस टाइम को ही दोबारा लिख देगा। हर चीज मिट जाएगी जैसे कुछ था ही नहीं। फिलहाल यह कैटास्ट्रॉफिक शिफ्ट नहीं हुआ, लेकिन इस पॉसिबिलिटी का वजूद ही इस बात का सबूत है कि यूनिवर्स का बुनियादी स्ट्रक्चर कितना फ्रेजाइल हो सकता है। वैक्यूम कैटास्ट्रोफी सिर्फ एक कैलकुलेशन एरर नहीं, ये एक रिमाइंडर है कि खाली स्पेस भी अपने अंदर अनेक सीक्रेट्स छुपाए हुए है, और उन सीक्रेट्स का राज जानना हो सकता है हमारी सबसे बड़ी डिस्कवरी या सबसे बड़ी तबाही। 0 पॉइंट एनर्जी एक्सप्लॉयटेशन। जरा सोचिए अगर एक ऐसी एनर्जी हो जो हर जगह हो, हवा में, खाली स्पेस में, हर एटम के बीच में, और हम उसे एक्सेस कर सकें। यह है 0 पॉइंट एनर्जी का वादा, एक ऐसी क्वांटम एनर्जी जो हमेशा मौजूद होती है, चाहे वैक्यूम हो या सब कुछ स्टैटिक लग रहा हो। यह आइडिया सिर्फ साइंस फिक्शन नहीं, ये क्वांटम फिजिक्स के दिल में छुपा एक फैसिनेटिंग कॉन्सेप्ट है। 0 पॉइंट एनर्जी अनफ्लक्चुएशंस का नतीजा है जो क्वांटम फील्ड्स में हर वक्त हो रहे होते हैं। इवन इन परफेक्ट वैक्यूम, पार्टिकल्स और एंटी पार्टिकल्स कंटिन्यूअसली पॉप इन एंड आउट ऑफ एग्जिस्टेंस। इन मूवमेंट्स की वजह से स्पेस कभी भी बिल्कुल खाली नहीं होता। ये हमेशा एक मिनिमम अमाउंट ऑफ एनर्जी रखता है जिसे हम 0 पॉइंट एनर्जी कहते हैं। अगर हम इस एनर्जी को हार्नेस कर सकें तो हमें कभी भी फ्यूल की जरूरत नहीं पड़ेगी। पावर प्लांट्स, बैटरीज, इवन रॉकेट्स, सबको एक इन्फिनिट क्लीन एनर्जी सोर्स मिल सकता है। मगर अब तक ये सिर्फ थियरी में ही है। कोई भी डिवाइस या मशीन इस एनर्जी को कैप्चर करने में कामयाब नहीं हुई। इसका सबब शायद ये है कि हम क्वांटम फील्ड्स को मैनिपुलेट करना अभी नहीं जानते। कुछ रिसर्चर्स कहते हैं कि जीरो पॉइंट एनर्जी को अनलॉक करने के लिए हमें स्पेस टाइम और क्वांटम लॉज का डीपर अंडरस्टैंडिंग चाहिए। शायद नए पार्टिकल्स या डायमेंशंस तक जाना पड़े। लेकिन जब तक वो अंडरस्टैंडिंग हासिल नहीं होती, ये एनर्जी एक इनविजिबल ट्रेजर की तरह छुपी रहेगी। एक खजाना जो सबके आसपास है मगर किसी के हाथ नहीं आता। जीरो पॉइंट एनर्जी एक्सप्लॉयटेशन का आइडिया एक रेवोल्यूशन शुरू कर सकता है, लेकिन तब तक ये सिर्फ एक सपना है, एक ऐसी फोर्स जो हमें फ्यूचर में एक नई दुनिया दे सकती है, लेकिन जिसे पकड़ना अभी मुश्किल है। अगर आप चाहें तो इन पार्ट्स को सेपरेट वीडियोस या सेगमेंट्स में भी तोड़ा जा सकता है, लेकिन मैंने पूरी स्क्रिप्ट आपके फ्लो के मुताबिक एक ही स्टाइल में लिखी है। अगला पार्ट भेजना चाहें तो रेडी हूं। Anti-gravity effects in superconductors. Picture this: materials floating in mid-air, completely unbound by gravity, hovering effortlessly as if lifted by an unseen force. It may sound like something straight from science fiction, but this idea isn't just imaginative storytelling. It's inspired by real observed phenomena involving superconductors. These extraordinary materials, when cooled to extremely low temperatures, don't just conduct electricity without resistance, they also exhibit one of the strangest behaviors in physics, the expulsion of magnetic fields, known as the Meissner effect. This property is what gives rise to the levitating effect, often mistaken for anti-gravity. When a superconductor is placed above a magnet, it pushes away the magnetic field, leading to a stable suspension above it. This interaction looks remarkably like gravity being defied. Yet despite decades of observing this behavior, scientists still grapple with understanding its deeper mechanisms. Could this levitation be more than a simple magnetic trick? Could it be the first glimpse into manipulating gravity? Some theories suggest that superconductors might one day be engineered into devices capable of creating gravitational shielding, effectively reducing the weight of objects or isolating them from Earth's gravitational pull. Such breakthroughs could revolutionize transportation or open the door to futuristic propulsion systems. But for now, we stand at the edge of understanding, staring into a mystery that continues to resist clear explanation. Cold fusion phenomenon. In 1989, the world of physics was shaken by a groundbreaking claim. Two electrochemists, Stanley Pons and Martin Fleischmann, announced that they had achieved nuclear fusion at room temperature. This process, dubbed cold fusion, was supposed to do what only the core of stars could: fuse atomic nuclei to release immense energy. But here it was, allegedly, occurring in a simple lab experiment, without the blistering heat of a star or hydrogen bomb. If true, it meant the dawn of virtually unlimited clean energy. The promise of cold fusion is staggering. It suggests a future where our energy needs are met without pollution, without fossil fuels, and without nuclear waste. But almost immediately after the announcement, doubt began to creep in. Scientists around the world scrambled to replicate the results, but most failed. Skepticism hardened. The scientific community labeled the findings premature. Some even called it pseudoscience. Still, some researchers didn't give up. Quietly, in labs across the globe, experiments continued. Strange anomalies popped up: unexplained heat, odd isotopes, unusual energy patterns, keeping the mystery alive. Could cold fusion be real, but just incredibly difficult to control or reproduce? Or was the original discovery simply a fluke, a misunderstood chemical reaction masquerading as nuclear fusion? Decades later, cold fusion sits in a strange place, half hope, half ghost story. It represents the possibility of a scientific breakthrough that could change the world, while also reminding us of how fragile and uncertain the frontier of discovery truly is. Sonoluminescence Paradox. What if sound could make light? In a darkened lab, a tiny bubble suspended in a liquid begins to shimmer. Then, with a sudden pulse of sound, it flashes, briefly, brilliantly, like a miniature star flickering in the dark. This bizarre phenomenon is called sonoluminescence, and its very existence challenges the boundaries of what we know about physics. At the heart of the mystery is this: when sound waves compress a gas bubble to extreme densities, it emits light. But how? The conditions inside the collapsing bubble are extreme. Some scientists estimate temperatures hotter than the surface of the sun. Yet there is no spark, no flame, no electrical input, just sound, and still, the bubble glows. The paradox only deepens when you try to account for where the energy comes from. Normally, creating light requires an energy source, chemical, electrical, or nuclear, but here, sound waves alone seem to create a transformation of energy that shouldn't be possible under classical laws. Is quantum physics at play here? Are we witnessing a microscopic energy conversion that hints at entirely new principles? Despite decades of study, sonoluminescence remains an unresolved mystery. Scientists have proposed a variety of explanations, from shockwave dynamics to quantum tunneling, but none have offered a complete, universally accepted answer. What we're left with is a glowing question mark, a bubble of mystery that continues to pulse in the dark, inviting us to look closer. Emission of X-rays from comets. When we think of comets, those icy wanderers of the solar system, we imagine cold, dusty trails, silent glides through space, and tails that sparkle in sunlight. What we don't expect is something violent or high energy. And yet, comets have been caught doing something astonishing, emitting X-rays. This form of radiation is usually associated with black holes, neutron stars, and supernovae, not frozen space rocks. The mystery was first uncovered in the 1990s with comet Hyakutake, and later confirmed in others like Hale-Bopp. These comets were found to be surrounded by clouds of high-energy X-rays, detectable from Earth. But how could this be? How does a comet, essentially a dirty snowball, emit such intense radiation? One theory points to the solar wind. As charged particles from the sun collide with the gases in the comet's coma, they might release bursts of energy. But this explanation feels incomplete. Why do only some comets emit X-rays? Why do the emissions vary so unpredictably? Perhaps something deeper is happening. An unknown interaction between the comet's material and solar particles, or a fundamental misunderstanding of how charged particles behave in space. Whatever the cause, the X-ray glow of comets remains one of the strangest and least understood mysteries in our solar system. Long-delayed echoes of radio signals. Imagine you're sending out a radio signal and hearing your own voice echo back, not in milliseconds as you'd expect, but several seconds later. This isn't science fiction. It's a real phenomenon, reported as early as the 1920s by stunned radio operators. Long-delayed echoes, or LDEs. These echoes didn't reflect off buildings or nearby structures. Instead, they returned after long, eerie gaps, sometimes 3, 5, even 15 seconds later. The signals seemed to vanish into space and return from nowhere. Theories abounded. Could they be bouncing off layers of the ionosphere, orbiting satellites, moon reflections? Each explanation accounted for some observations, but not all. What makes LDEs so strange is their unpredictability. Sometimes they happen, sometimes they don't. Sometimes they come from one frequency but not another. Some researchers have even suggested they might be echoes from deep space, reflected off unknown objects or phenomena we haven't yet discovered. Are these signals hinting at hidden structures in the atmosphere or unknown properties of electromagnetic waves? Could they even be the result of exotic space-time distortions? Whatever the truth, the long-delayed echoes remain one of the strangest and least resolved anomalies in radio science, a ghost signal that refuses to be explained. Fast radio burst patterns. In the vast fabric of space, a strange and electrifying signal continues to confound scientists, fast radio bursts, or FRBs. These are millisecond-long flashes of intense radio waves that somehow release more energy in that brief moment than our sun emits in an entire day. The sheer power packed into such a short time has left astrophysicists scrambling for answers. First discovered in 2007, these bursts seemed like cosmic anomalies. But as more of them were detected, patterns began to emerge. Some FRBs appeared randomly, while others repeated in intervals, as though something was timing them. This repeating behavior is what really deepens the mystery. It suggests that FRBs might not just be chaotic explosions in deep space. They might be linked to predictable events, perhaps highly magnetized neutron stars, merging remnants, or energy being ejected from black holes. Some scientists speculate on even wilder possibilities, like the signals being sent by advanced alien civilizations. While that's a long shot, The structured nature of some FRBs forces us to entertain every possibility. Are we simply witnessing extreme astrophysical processes, or is something entirely new behind these bursts? The mystery remains, and with every new signal, our understanding of the universe is stretched further. Neutron star glitches. Neutron stars, dense collapsed cores of massive stars, are among the most extreme objects in the universe. Despite being just a few kilometers wide, they pack more mass than our Sun. They spin incredibly fast and emit beams of radiation we observe as pulses. But every so often, these stars exhibit an unexplained phenomenon, sudden glitches in their spin rate. These glitches, which can be subtle or dramatic, disrupt the normally consistent rhythm of a pulsar's signal, leaving researchers puzzled. What causes these abrupt changes? One theory suggests that the crust of the neutron star cracks under immense pressure, suddenly shifting the rotation. Another idea points to changes in the star's superfluid core, an exotic state of matter with almost no resistance. But none of these theories can explain every observed glitch. Some researchers even believe that unknown quantum forces or physics beyond our current models might be involved. These glitches hint at something deeper happening within neutron stars, perhaps something that could one day reveal entirely new layers of physical reality. Strange pulsar signals. Pulsars, the rotating beacons of the cosmos, usually emit signals with clock-like precision, but sometimes they don't. In 2018, astronomers detected a pulsar that behaved unpredictably, emitting irregular bursts with unexpected gaps and shifts. Unlike the steady signals scientists are used to, these bursts suggested that something was interfering with the pulsar's natural emission. The cause is still up for debate. Could it be a hidden companion object? Could internal magnetic fields be fluctuating in unusual ways? Some propose that the crust of the pulsar might be deforming and affecting how radiation escapes. But there's also the possibility that we're observing new physics, perhaps influenced by dark matter or unexplored interactions in quantum fields. These strange pulsar signals could be a window into unseen forces that are shaping not just stars, but the very structure of space itself. Ultra-high-energy neutrinos. Neutrinos are among the most mysterious particles in the universe. Most pass through us undetected, originating from deep cosmic sources. But then there are ultra-high-energy neutrinos, rare particles so powerful they challenge our very understanding of physics. Detected by observatories like IceCube in Antarctica, these neutrinos carry energies far beyond those seen in typical cosmic events. Where do they come from? Some point to black holes or gamma-ray bursts as possible sources, but none of these fully explain how the neutrinos retain their immense energy over such vast distances. Some theories even suggest they're linked to dark matter or phenomena from the early universe. These particles pierce the cosmos with precision, and every time we detect one, we're reminded how little we truly know about the extreme forces shaping the universe. GZK limit. Cosmic rays, high-energy particles zooming through space are well studied, but some of them defy expectations. According to the GZK limit, these particles should lose energy as they collide with the cosmic microwave background radiation. They shouldn't be able to travel more than 100 million light-years. And yet, some ultra-high-energy cosmic rays make it to Earth from far beyond that distance. This apparent violation of a fundamental cosmic rule has baffled physicists. Are these particles being generated closer than we think, or are they bypassing known limitations through mechanisms we don't yet understand? Some theories invoke unknown particles or even dark matter. These rogue cosmic rays hint at a deeper structure to the universe, something that operates outside of our current models, potentially changing how we view the fundamental workings of space-time. Hyperspace jump theories. Imagine crossing the unimaginable distances of space in an instant. No rockets, no months-long travel, just a leap from one point in the universe to another. This is the compelling vision behind hyperspace jump theories. It may sound like pure science fiction, yet it's a topic that has stirred the curiosity of physicists for decades. The core idea proposes that it might be possible to fold or manipulate the fabric of space-time, allowing for faster-than-light movement without actually breaking the known laws of physics. Instead of traveling in a straight line through three-dimensional space, a spacecraft could access a higher-dimensional hyperspace, essentially taking a shortcut across the cosmos. One of the most intriguing interpretations of this is the concept of wormholes, hypothetical tunnels that connect two distant points in space-time. In theory, entering one side of a wormhole near Earth could result in emerging near a distant galaxy. However, we have yet to detect a real wormhole, and the physics behind stabilizing one for human travel remains uncertain and deeply complex. Another proposed method involves warp drives, such as the Alcubierre drive, which would contract space in front of a vessel while expanding it behind, creating a bubble that rides on space-time itself. Technically, the ship wouldn't move faster than light, but the space around it would. Unfortunately, such a drive would require enormous amounts of exotic matter or negative energy, something not currently achievable. Beyond the technical limitations, hyperspace theories raise philosophical questions too. Are there dimensions beyond the ones we perceive? Is it possible that the universe itself holds natural pathways, shortcuts hidden within its very design? Hyperspace jump theories not only fuel the imagination, but also push the limits of physics, suggesting that maybe, just maybe, faster-than-light travel is buried somewhere within the universe's blueprint, waiting to be uncovered by future discoveries. Cosmological lithium problem. After the Big Bang, the universe was a boiling soup of particles. As it cooled, the first light elements formed: hydrogen, helium, and lithium. This period, called Big Bang nucleosynthesis, laid the foundation for the cosmos. But here's the conundrum. While the predicted amounts of hydrogen and helium in the universe match what we observe, lithium doesn't. There's far less of it, especially in the oldest stars, than theory suggests. This is known as the cosmological lithium problem. According to our best models, early universe conditions should have produced 3 times more lithium-7 than we see today. This isn't just a minor math error. It suggests something fundamental is missing from our understanding of how elements formed. Some scientists propose that old stars might destroy lithium through fusion, but this doesn't account for the uniform lithium shortfall across many ancient stars. Others think that perhaps our models of the early universe are flawed or incomplete. More exotic theories point toward new physics, maybe particles or forces, that affected nuclear reactions in the early universe in ways we haven't yet discovered. Could there have been an unknown phase in the early universe's evolution, or even interactions with dark matter? This elemental mystery may seem minor compared to black holes or dark energy, but it touches the core of cosmology. If we can't account for something as basic as lithium, it casts doubt on other predictions from the Big Bang model. The lithium problem remains unresolved, reminding us that even in the earliest moments of creation, the universe may have been hiding secrets we've yet to fully decode. Simulation hypothesis backed by physics. What if reality as we know it, everything we see, touch, and feel, isn't truly real? What if it's all part of a sophisticated simulation so perfectly crafted that we cannot tell the difference? This is the central idea behind the simulation hypothesis, a theory that has moved from speculative fiction into serious academic conversation with surprising support from modern physics. At the heart of the theory is a question about consciousness and perception. Could an advanced civilization create a simulated universe indistinguishable from reality? In today's world, we simulate environments all the time: virtual reality, video games, weather models. As our computing power grows exponentially, the idea that a civilization could simulate entire universes doesn't seem so far-fetched. Supporters of the hypothesis often point to quantum mechanics. In the quantum world, particles behave in strange ways. They can exist in multiple states at once, and their behavior often changes depending on whether they are being observed. This observer effect leads some to believe that the universe may only render what's being looked at, much like how a computer game only shows what's on screen to save processing power. Could this be a sign that we are part of a cosmic program? Another argument involves the limits of computation itself. If technological advancement continues indefinitely, then at some point in the future, it might be possible to simulate not just individuals, but entire civilizations and realities. Statistically, if even one such simulation exists, it's possible we're already living inside one. Though there is no concrete evidence yet, the simulation hypothesis challenges our deepest assumptions about existence. If the universe is an artificial construct, what or who is outside of it? And can we ever detect or escape the bounds of the simulation? These questions lie at the intersection of science, technology, and philosophy, leading us to confront the very nature of reality. Retrocausality. Imagine a universe where the future can influence the past, a world where events don't necessarily follow the strict arrow of time we've come to understand. This is the strange idea behind retrocausality, a theory that suggests that causation might work in reverse, and that future outcomes could affect past actions. In everyday life, causality is straightforward. You flip a switch and the light turns on. But in the quantum world, things aren't so simple. Particles can exist in superpositions, multiple states at once, and their behavior often appears random. But what if that randomness isn't randomness at all? What if what we observe in the present is somehow shaped by what happens in the future? Quantum entanglement adds another layer to this mystery. When two particles are entangled, they appear to affect each other instantly, no matter how far apart they are. Some physicists propose that this strange connection might be explained by retrocausality, that the measurement of one particle in the future could influence the state of another in the past. This theory turns our understanding of time on its head. If true, it might mean time isn't a one-way street, but a complex loop where past and future interact in ways we don't yet understand. It raises perplexing questions. Could information travel backward in time? Could decisions made in the future alter the outcome of past events? Though highly controversial and still theoretical, retrocausality is gaining attention as physicists continue to explore the boundaries of quantum mechanics. It challenges not just our scientific models, but also our philosophical notions of free will, determinism, and the flow of time. For now, it remains a compelling mystery that invites us to rethink everything we know about causality and the structure of reality itself. Closed time-like curves. Time travel has fascinated humanity for generations, appearing in everything from ancient myths to modern science fiction. But what if the concept isn't entirely fiction? In the world of theoretical physics, there's a bizarre idea known as closed time-like curves, or CTCs, hypothetical paths through spacetime that loop back on themselves, theoretically allowing one to travel into their own past. Einstein's theory of general relativity provides the mathematical framework for such curves. According to the theory, massive objects can warp spacetime. Under certain extreme conditions, such as near-rotating black holes or hypothetical constructs like cosmic strings, spacetime might curve enough to create a closed loop in time. Visualize it like drawing a circle in spacetime. Instead of moving forward in a straight line, you spiral around and end up at your starting point, not just in space but in time. This means, in theory, someone could revisit a moment from their past. However, this concept introduces serious paradoxes, such as the grandfather paradox, where changing something in the past could prevent your own existence. Some researchers suggest that nature might prevent these paradoxes through self-consistency, only allowing time loops where events cannot be altered in a way that would create contradictions. Others believe closed time-like curves might connect to alternate timelines or dimensions, where actions in one loop don't affect the original timeline. Despite being purely theoretical, the idea of CTCs provides a fascinating lens through which to examine the flexibility of time. Could time be a loop, or at least contain loops? Could there be parts of the universe where the past, present, and future coexist in ways we cannot yet comprehend? While there is no experimental evidence, closed time-like curves remain one of the most thought-provoking possibilities in physics. Tachyons, faster-than-light particles. In the vast framework of physics, one rule has remained unbroken: nothing can move faster than light. This speed limit, defined by Einstein's theory of special relativity, is a foundational element of modern science. Yet theoretical physics has imagined a particle that defies this rule, the tachyon. Tachyons are hypothetical particles that always move faster than light. They are predicted to have imaginary mass, a concept that challenges our conventional understanding of matter and energy. Because of this, tachyons can only exist at speeds beyond light, and they can never slow down to the speed of light or below. It's a wild idea, and one that introduces significant complexities into physics. So far, tachyons have never been observed. However, they do appear in certain mathematical models in quantum field theory and string theory. This keeps them in the realm of possibility, even if they remain undetected. Some physicists speculate that if tachyons do exist, they could provide answers to several unsolved mysteries, perhaps even contributing to our understanding of dark matter or quantum entanglement. An even stranger implication is the idea that tachyons could travel backward in time. If they exceed the speed of light, and then in some reference frames, they would appear to arrive before they depart, leading to causality violations. Could tachyons offer a new route to time travel, or are they simply mathematical ghosts with no physical reality? The mystery of tachyons continues to captivate researchers. They serve as a reminder that the laws of physics as we know them might only be part of a much larger, more complex picture, one that includes particles and forces we haven't yet discovered, in dimensions we cannot yet perceive. Pioneer Plaque Misinterpretation Hypothesis. In 1972, humanity launched a bold message into the cosmos, a greeting card for the universe etched onto the Pioneer 10 spacecraft. This metal plaque carried drawings of a man and a woman, a schematic of our solar system and mathematical clues meant to identify our home and species. Designed by Frank Drake and Carl Sagan, it was a calculated effort to communicate with extraterrestrial intelligence using what they believed to be universal symbols. But what if those symbols aren't so universal after all? This unsettling idea is at the heart of the Pioneer Plaque Misinterpretation Hypothesis. The notion suggests that alien beings, should they find the plaque, might interpret its contents in ways entirely different from our intentions. We assume they'll understand the diagrams based on shared logic or physics, but intelligence evolved under alien biology, and cognition may interpret signs and symbols in ways we can't even imagine. A simple image of a human might be seen not as a friendly introduction but as a warning, a symbol of power, or even a threat. Consider the diagram that pinpoints Earth's location using pulsars. To us, it's a clever cosmic map, but to an alien species with a different grasp of astronomy, or none at all, it could be meaningless or misdirecting. Even the binary-coded hydrogen atom might be misread if their concept of matter or structure differs from ours. What we view as clear, universal communication might come across as cryptic or dangerous. The plaque's human figure, for instance, might raise more questions than it answers. Is it a biological being? A deity? A tool? Could the raised hand be seen as a symbol of dominance rather than peace? If alien civilizations are out there, there's no guarantee they'll decode the plaque the way we hope. Instead of forming a connection, our message could sow confusion, caution, or even fear. As Pioneer 10 drifts deeper into space, the plaque it carries becomes not just a symbol of human ambition, but a reminder of how difficult true communication can be across the stars. In trying to make contact, we may have sent out a puzzle rather than a greeting, and that puzzle may never be solved the way we intended. Non-quantized redshift light traveling through space is more than illumination. It's a carrier of deep cosmic information. One of the most critical tools astronomers use to measure the universe is redshift, the stretching of light wavelengths as distant objects move away from us. For decades, this phenomenon has confirmed the expansion of the universe. But what happens when the pattern breaks? This is the mystery of non-quantized redshift, an anomaly that's stirring fundamental questions in cosmology. Ordinarily, redshift follows a predictable pattern. The farther away a galaxy, the more its light shifts toward red. But some galaxies don't fit this rule. Instead of a smooth, continuous change, their redshift appears in sudden jumps, as if space itself operates in discrete steps rather than a seamless flow. These unusual observations suggest that light might not behave in entirely linear ways, hinting at unknown mechanisms within the fabric of space. This raises the provocative possibility that redshift may not be purely a product of motion or cosmic expansion. Could these irregular shifts point to interactions we don't yet understand, perhaps involving dark matter, unknown forces, or hidden dimensions? Some theorists propose that these jumps could reflect layered structures in the universe or discontinuities in space-time itself. If non-quantized redshift is real and not a measurement error, the implications are enormous. It could mean that our foundational model of cosmic expansion needs re-evaluation. Perhaps the universe isn't expanding smoothly at all, but pulsing in discrete patterns. Or maybe redshift includes influences beyond velocity, like gravitational interference or energy transitions on a universal scale. This mystery forces us to reconsider how we measure and interpret the universe. It suggests that space might be stranger and more structured than previously imagined, challenging the continuous model that's shaped modern astrophysics. Non-quantized redshift isn't just a data quirk. It might be a sign that a deeper cosmic truth awaits discovery. UV catastrophe. At the dawn of the 20th century, classical physics was nearing its peak, until a perplexing anomaly almost tore it apart. Known as the ultraviolet catastrophe, this problem emerged when scientists tried to predict how much radiation objects emit at various wavelengths. According to established theory, radiation should increase infinitely at shorter wavelengths, especially in the ultraviolet range. But that prediction didn't match reality. It was, quite literally, a catastrophe. This paradox arose from experiments involving blackbody radiation, how objects emit energy based on temperature. When calculations were applied using classical formulas, they predicted infinite energy at high frequencies. But in the real world, such energy levels never appeared. This disconnect signaled that something fundamental in our understanding of physics was deeply flawed. Enter Max Planck, who proposed a radical solution. Energy is not continuous but comes in discrete packets, quanta. This idea defied centuries of scientific thought, but it resolved the ultraviolet catastrophe perfectly. Instead of energy rising without bound, Planck's quantum theory imposed limits, aligning predictions with observed results. What began as a theoretical disaster ultimately became the birth of quantum mechanics. The ultraviolet catastrophe marked a turning point in science. It revealed that nature behaves differently on the atomic scale, and that energy, light, and matter all follow rules that classical physics couldn't explain. Planck's insight not only solved a specific problem, it opened the door to quantum theory, leading to revolutions in technology, chemistry, and our understanding of reality itself. What started as a broken equation in a physics lab became a bridge to the quantum world. The ultraviolet catastrophe is a reminder that great scientific progress often begins with confronting the mysteries we least understand. N-rays controversy. In 1903, a French physicist named René Blondelot announced a groundbreaking discovery, a new form of radiation he called N-rays. He claimed that this invisible energy, emitted by most substances, could influence light and even change how materials behaved. The idea caught on quickly, at least in France, and soon dozens of scientists claimed to observe these strange rays. But within a few years, the N-ray phenomenon unraveled into one of the most revealing controversies in scientific history. Blondelot's experiments seemed to show that N-rays could increase the brightness of a light source when passed through certain materials. He believed they were a new addition to the electromagnetic spectrum. However, replication efforts by scientists outside his circle failed repeatedly. Something wasn't adding up. The turning point came when American physicist Robert W. Wood attended one of Blondelot's demonstrations. Secretly, he removed a critical prism from the experimental setup without telling Blondelot. Astonishingly, Blondelot continued to report the same results, despite the key component being missing. This indicated that the observed effects weren't real, but psychological, a case of confirmation bias. Eventually, the scientific community accepted that N-rays were an illusion, not a discovery. But the controversy highlighted a deeper lesson. Even well-intentioned scientists can be misled by their expectations. The N-ray saga became a cautionary tale about the importance of independent verification, skepticism, and the potential pitfalls of human perception in the scientific process. Though N-rays never existed, the episode left behind a powerful message. In the search for truth, belief must always be tested against evidence. The impossible EM drive. Imagine a spacecraft capable of reaching distant stars without carrying a single drop of fuel. No propellant tanks, no exhaust flames, just silent, continuous motion through the void. This is the promise of the EM drive, a controversial invention that defies everything we thought we knew about physics. If real, it could revolutionize space exploration, but that "if" remains one of the biggest mysteries in modern science. Invented in 2001 by British engineer Roger Scheuer, the EM drive is a sealed device that supposedly generates thrust by bouncing microwaves inside a conical cavity. Unlike traditional engines that push against expelled mass, the EM drive claims to push against nothing. It appears to violate Newton's third law of motion and the conservation of momentum, laws considered unbreakable in physics. Despite widespread skepticism, the EM drive caught serious attention in 2014 when NASA's EagleWorks lab reported detecting a small amount of thrust during experiments. The thrust was tiny but measurable, sparking renewed excitement and debate. Was it a real effect or an artifact of flawed measurements? Researchers couldn't fully explain it, but they also couldn't dismiss it outright. If the EM drive works, it would mean propulsion without fuel, a game changer for long-duration space travel. It could drastically reduce mission costs, allow interstellar travel, and even enable constant acceleration through space. But the theory behind it lacks grounding in accepted physics. Some speculate it might involve quantum vacuum fluctuations or exotic interactions with spacetime, but nothing conclusive has emerged. Today, the EM drive remains in limbo, tested, doubted, and never fully explained. It challenges our understanding of motion and energy, and perhaps, if validated, could usher in a new era of exploration. For now, it exists as one of science's strangest paradoxes, a potential revolution waiting on the edge of belief. Woodward Effect. In the world of theoretical physics, there are some ideas so radical, so game-changing, that if proven, they could alter the entire landscape of science and technology. One such mystery is the Woodward Effect, a concept that promises the possibility of motion without the need for traditional propulsion. No rockets, no fuel, just a pure, reactionless push into space. It all began with physicist James Woodward, who proposed a theory rooted in subtle but powerful aspects of general relativity. According to Woodward, under certain conditions involving rapid energy changes, objects might undergo mass fluctuations, temporary changes in their inertial mass. If these fluctuations are carefully timed and manipulated using electromagnetic fields, they could result in a net force, or thrust, without expelling mass. This is what we now call the Woodward Effect. At first glance, this idea seems impossible. After all, Newton's third law states that every action must have an equal and opposite reaction. How can something move without pushing against anything? Yet Woodward's hypothesis challenges that principle in a fascinating way, suggesting that the inertia of an object, its resistance to acceleration, is tied not just to its own mass, but to the mass of the entire universe. This concept, known as Mach's principle, hints that inertial effects are influenced by far-off matter in the cosmos. Testing the Woodward effect has proven difficult. Some researchers, including Woodward himself, have built devices, Mach effect thrusters, that appear to generate tiny amounts of thrust under laboratory conditions. But these results remain controversial. The measured forces are small, and critics argue they could be caused by thermal expansion, electromagnetic interference, or other mundane effects. Yet the experiments continue, driven by the tantalizing potential of the theory. If the Woodward effect is real, it could revolutionize how we explore space. Spacecraft could move without carrying vast amounts of fuel, relying instead on electrical energy to produce motion. Missions to Mars, deep space, or even interstellar journeys could become far more feasible. But for now, the Woodward effect remains unproven, a whisper of a new physics waiting to be confirmed or debunked. Klein-Gordon negative probability. In the bizarre and often paradoxical world of quantum mechanics, our most basic assumptions are constantly being tested. One of the most perplexing anomalies arises from the Klein-Gordon equation, a mathematical tool used to describe particles moving at relativistic speeds. What makes it so mysterious is that in certain situations, this equation yields something that seems utterly impossible: negative probability. The Klein-Gordon equation was one of the first attempts to reconcile quantum mechanics with special relativity. It was developed to describe scalar particles like mesons and is still used in modern quantum field theory. Yet when physicists began analyzing it in detail, they noticed something strange. Unlike standard quantum equations, which yield positive definite probabilities, as all probabilities should, the Klein-Gordon equation sometimes produced negative values. This is deeply troubling because in classical and quantum probability, negative values make no physical sense. Probability is the chance of something happening. It should always be between 0 and 1. A negative probability suggests a less than impossible event, which defies logic. So what does it mean? Some scientists believe these negative values don't represent physical probabilities, but are instead a byproduct of how the equation handles time and energy. In certain interpretations, they might represent advanced wave solutions, particles moving backward in time. Others suggest that negative probabilities hint at a deeper layer of quantum reality, one not yet fully understood. The Klein-Gordon anomaly is more than just a mathematical quirk. It challenges our assumptions about causality, determinism, and even the fabric of space-time itself. Are these negative values just errors in our models, or glimpses into a hidden realm of physics? The answer is still out of reach, but the mystery reminds us that our understanding of reality is always evolving, and sometimes the math leads us into truly strange territory. Causality violations in quantum mechanics. In everyday life, cause precedes effect. We flip a switch and the light turns on. We push a ball and it rolls forward. This sequence of events, cause and then effect, is known as causality, and it forms the bedrock of classical physics. But in the realm of quantum mechanics, that principle starts to fall apart in strange and often unsettling ways. Causality violations in quantum mechanics refer to phenomena where the usual flow of time, past to present to future, seems to blur or even reverse. One of the most famous examples is quantum entanglement. When two particles become entangled, a measurement on one instantly affects the state of the other, regardless of the distance between them. This happens so quickly that it appears to defy the speed of light and suggests a kind of influence that travels outside of normal spacetime. Even more bizarre is the idea that some quantum processes might involve retrocausality, effects influencing their causes. In certain interpretations of quantum theory, like the two-state vector formalism, events in the future can influence the present, and outcomes can depend on both past and future boundary conditions. In experiments like the delayed choice quantum eraser, the way we observe a particle can seemingly affect its earlier behavior. These causality violations don't just confuse scientists, they challenge the entire structure of how we think the universe works. If time doesn't always flow forward, what does that say about free will, determinism, or the possibility of time travel? Of course, not all physicists agree that causality is truly violated. Some argue that what looks like backward causation is just a misinterpretation of quantum statistics. But the debate is far from settled, and the more we study the quantum world, the more we find our classical intuitions failing. In this quantum twilight zone, reality is not just stranger than we imagine, it may be stranger than we can imagine, and the puzzle of causality violations may be the key to unlocking the true nature of time itself. Transplanckian Problem. There exists a boundary in physics so small, so fundamental, that to cross it is to leave behind everything we know about how the universe works. This is the Planck scale, the realm where the size and energy of particles approach the limits set by quantum gravity. Beyond this boundary lies a deep mystery known as the Transplanckian Problem. The Planck length, about 1.6 cast 10 to 35 meters, is considered the smallest meaningful unit of space. At this scale, the smooth fabric of spacetime becomes turbulent and foamy. Our classical descriptions of geometry break down and quantum effects dominate. But here's the problem. Some theoretical models, especially in cosmology and black hole physics, suggest that physical processes involve scales even smaller than the Planck length. This creates a paradox. If physics breaks down at the Planck scale, how can our theories describe things that go beyond it? For instance, during the early moments of the Big Bang, quantum fluctuations smaller than the Planck length may have influenced the formation of galaxies. Similarly, in black hole evaporation, particles that emerge from the event horizon may have origins in the Transplanckian regime. We currently lack a theory of quantum gravity that can handle these extreme conditions. String theory, loop quantum gravity, and other models offer possible solutions, but none have been confirmed. The Transplanckian problem isn't just about ultra-small distances, it's about the limits of what physics can currently describe. Until we can peer into this tiny, mysterious realm, we're left with unanswered questions. What happens beyond the Planck scale? Does space-time itself cease to exist, or do new, unimaginable laws of nature take over? The answers could reshape our understanding of the universe from its earliest moments to the edges of black holes. Quantized inertia theory. Imagine a theory that doesn't just tweak existing physics, but rewrites the rules entirely. That's the promise of quantized inertia, a bold and controversial idea that offers an alternative to both dark matter and standard models of motion. If correct, it could explain some of the universe's biggest mysteries and even offer a path to futuristic propulsion systems. Proposed by physicist Mike McCulloch in 2007, quantized inertia challenges the way we understand inertia, the resistance an object has to changes in motion. In Newtonian mechanics, inertia is tied directly to mass. But McCulloch argues that inertia might actually emerge from quantum effects on a cosmic scale. According to the theory, when objects accelerate, they interact with unruh radiation, a type of quantum energy that appears when objects move relative to empty space. In McCulloch's model, this radiation is constrained by the size of the observable universe. The result? A quantized, modified form of inertia that changes under certain cosmic conditions. This leads to a fascinating possibility. Quantized inertia could explain why galaxies spin the way they do, without needing dark matter. For decades, astronomers have observed that galaxies rotate faster than expected based on their visible mass. The conventional answer has been to assume the presence of invisible dark matter, but quantized inertia offers a different explanation. Maybe inertia itself changes on large scales. Even more exciting is the theory's implication for propulsion. If inertia can be modified, then perhaps spacecraft could be moved using only energy, without fuel. This would be a breakthrough for space exploration, allowing for efficient long-distance travel. Quantized inertia is still speculative and has not been widely accepted. Critics argue that it lacks sufficient experimental support and that its assumptions may be oversimplified. But its elegance and its potential keep the conversation going. Could it be the key to a deeper understanding of motion, inertia, and the cosmos itself? The mystery remains, waiting to be explored. Theoretical magnetic monopole. Imagine holding a magnet in your hand, the kind that sticks to your fridge or attracts metal. You know it has two poles, a north and a south. That's just how magnets work. But now, picture something wildly different. A magnet with only one pole. Just a north or just a south, no pair, no opposite. That's the mind-bending idea behind the magnetic monopole, a concept so strange, so elusive, that it has puzzled physicists for generations. A magnetic monopole is, in theory, a particle that carries only a single magnetic charge. Unlike any known magnet, it wouldn't have a counterpart pole. And if such particles exist, they could revolutionize how we understand electromagnetism, one of the four fundamental forces that shape our universe. The mystery began in the 1930s when Paul Dirac, a brilliant physicist, proposed that magnetic monopoles could exist. He wasn't just making things up. His mathematical models suggested that the existence of even one monopole could explain a deep riddle of nature, why electric charge always appears in fixed, discrete quantities. The world, it seems, is quantized, and a magnetic monopole might be the key to explaining why. Despite decades of searching, no one has ever found one. Not in labs, not in particle accelerators, not even in the farthest reaches of space. Yet some physicists haven't given up. They believe that monopoles might exist under extreme conditions, maybe in the fiery hearts of neutron stars or in the chaos of high-energy particle collisions. The idea remains unconfirmed, and some even wonder if it's just a mathematical artifact, a beautiful idea with no physical form. Still, the magnetic monopole remains one of the most intriguing mysteries in modern physics. Could we be missing something fundamental? Could a single-pole particle be hiding in plain sight, waiting to change our understanding of reality? Until it's discovered, the search continues, a quest driven by the hope that one anomaly might unlock a new era of scientific discovery. Anomalous solar neutrino behavior. The sun. It gives us warmth, life, and light. But behind its bright glow lies a strange enigma that haunted scientists for decades: the mystery of solar neutrinos. Neutrinos are ghostly particles, created in staggering numbers during the nuclear fusion reactions inside the sun's core. They are unimaginably small, fast, and nearly impossible to detect. Trillions pass through your body every second, yet you'll never feel them. Scientists curious about the sun's internal workings began building sensitive detectors deep underground to catch just a few of these elusive messengers. But something didn't add up. When the first neutrino detectors were turned on, they found only about 1/3 of the expected number. Where were the missing neutrinos? Were the sun's models wrong, or was something stranger happening? This puzzle became known as the solar neutrino problem. For over 40 years, it baffled researchers, but then a breakthrough changed everything. Scientists discovered that neutrinos could actually switch identities, changing from one flavor to another as they traveled through space. This transformation made them invisible to early detectors, which were only looking for one specific type. This phenomenon, neutrino oscillation, not only solved the mystery but also revealed something profound. Neutrinos have mass. This went against the original predictions of the standard model of particle physics. The discovery opened a door into a hidden world of physics, where even the smallest particles behave in mysterious ways. And yet, the mystery isn't entirely solved. Scientists are still trying to understand how and why these particles shift forms. Could their behavior reveal deeper forces at play in the universe? Might they carry clues to the dark energy or unseen dimensions? The strange case of solar neutrinos reminds us that even our closest star holds secrets, and sometimes it's the smallest particles that whisper the biggest truths about the universe. Levitating plasma clouds. Now imagine standing inside a high-tech lab, watching a glowing cloud of gas, not inside a container, not held by wires, but hovering freely in the air. No strings, no supports, just a luminous, pulsating plasma cloud defying gravity. Welcome to the strange world of levitating plasma clouds, a phenomenon that sits at the edge of modern science. Plasma, often called the fourth state of matter, is a superheated gas of charged particles, found everywhere from neon signs to stars. But controlling plasma, especially in a stable, floating form, is a scientific challenge. Yet under certain extreme conditions, scientists have witnessed plasma suspending itself in air, as though held in an invisible hand. These clouds hover in place, shaped and controlled by electromagnetic fields that trap the charged particles in a delicate, glowing balance. But the question that haunts researchers is this: how do these electromagnetic fields maintain such precision? What mechanisms allow the plasma to resist gravity, motion, and dispersion? How do the particles within the cloud organize themselves in such a structured way? Some believe that this phenomenon could offer insights into fusion energy, the same power that fuels the stars. Others wonder if understanding plasma levitation might lead to new propulsion technologies, using magnetic fields to manipulate matter in ways we can barely imagine. Still, many aspects remain unexplained. The levitating plasma cloud is more than a scientific curiosity. It's a mystery that could hold keys to the future of clean energy, transportation, or even how matter behaves under exotic conditions. In a world where we think we understand the rules, these floating clouds challenge our assumptions. What keeps them afloat? What secrets do they hold? The answers may be hidden within the charged chaos of their glowing forms, waiting to illuminate the future. Anomalous magnetic dipole moments. Electrons are among the most well-understood particles in physics, or so we thought. For decades we believed we had nailed down their behavior, but a strange inconsistency has emerged, one that might shake the very foundations of quantum theory. This is the mystery of anomalous magnetic dipole moments, a tiny, unexpected deviation in the magnetic behavior of particles like electrons and muons. In quantum mechanics, the magnetic dipole moment describes how a particle interacts with magnetic fields, and it's deeply tied to its spin. The Standard Model predicted its value with great precision, but when scientists measured the electron's magnetic dipole moment to extreme accuracy, they found something slightly off. It was a tiny difference, almost insignificant, but it didn't go away. The same happened with muons. Newer, more advanced experiments confirmed the anomaly. The implication: there might be something influencing these particles, something our current physics can't explain. Could this be evidence of a new force, an undiscovered particle, or perhaps a flaw in our cherished theories? Some physicists believe that the anomaly could point towards supersymmetry, a theoretical framework suggesting that every known particle has a hidden superpartner. Others propose that we may be brushing against the edge of an entirely new layer of reality, a hidden realm of particles and forces yet to be discovered. For now, we don't know. But the tiniest anomaly may yet lead to the biggest revelations. As our measurements grow more precise and our experiments more ambitious, we inch closer to answers, and perhaps to rewriting the laws of physics themselves. Strange matter contagion hypothesis. In the shadowy corridors of theoretical physics, there exists an idea so bizarre, so chilling, that it sounds like something from the pages of science fiction. Yet it's rooted in serious scientific speculation. It's called the strange matter contagion hypothesis, and it suggests that a strange form of matter could spread like a cosmic infection, transforming everything in its path. Strange matter is a hypothetical substance made of strange quarks, particles found in the crushing density of neutron stars. Unlike regular matter, strange matter may be more stable under certain conditions. If that's true, then it poses a terrifying question. What happens if a tiny droplet of strange matter comes into contact with regular matter? The hypothesis says this could trigger a chain reaction. One particle becomes strange, then another. Like a virus, it spreads, converting atoms, planets, stars, even entire galaxies, into something unrecognizable. It's a doomsday scenario that sounds like fantasy, but in certain high-energy environments, like during neutron star collisions or particle accelerator experiments, the creation of strange matter isn't entirely out of the question. Is it likely? Perhaps not, but possible. Some physicists believe so. The strange matter contagion hypothesis challenges our understanding of matter's stability. It forces us to consider whether the matter that makes up everything we see is actually the most stable form, or whether there's a deeper, more dangerous state waiting to be uncovered. Until we know for sure, this strange silent threat lingers in the theoretical ether, an eerie reminder that the universe still holds secrets capable of reshaping everything.